Thanks everyone for joining the stream. Hello, and today we'll continue discussing stochastic processes in science and engineering, in particular about Brownian motions. So last time we discussed Einstein's and Smoluchowski's approach to Brownian motion. So here, so in the process we introduced the foreshadowing, so to say, of what comes next, in particular the theory of Markov process. So Einstein's argument and Smoluchowski's argument essentially paved the way of studying a Markov process using the master's equation. Okay, but today we're gonna take a look at the same phenomenon, aka Brownian motion, from a different angle. That is through the work of Langevin and Ornstein and Ulenbeck. Okay, so these two fellows, their work initiated the study of stochastic differential equation. And speaking of which, this Saturday we will have a live stream on introduction to stochastic differential equations for applied scientists. That is to say, we will introduce the subject intuitively without heavy usage of measure theory or even measure theory at all. Okay, so it's going to be very exciting. So right now, because we're also have ongoing series on PDEs, and I think it will be interesting to pair that with stochastic differential equations, because eventually, as we'll see, the two are very much related. Okay, so each are, of course, massive fields. Stochastic differential equation and partial differential equations are very much related, and this will culminate in our discussion on Fokker-Planck equation. So Fokker-Planck equation is a partial differential equation that governs the probability density of the solution to stochastic differential equation. So that's a very rough description, but basically we want to do these lives simultaneously sort of concurrently, so that the connection between the fields became apparent. So without further ado, let's just get to today's main topic, Brownian motion according to Langevin and Ornstein-Ulenbeck. Let's go. Paul Langevin, French, not mathematician but physicist. Okay, so Paul Langevin here. After a few years after Einstein and Smoluchowski's work, a new method for studying Brownian motion was developed by Paul Langevin. Langevin arrived at the same results for the mean square displacement as Einstein. So remember what this means. What is the mean square displacement Einstein obtained? Well, it's here. So by deriving the diffusion equation, diffusion equation through a stochastic lens, Einstein arrived at the displacement mean square formula. The mean square the square root of the arithmetic mean of the square of the displacement. So essentially this is a standard deviation because the mean is 0. The standard deviation of the displacement in Brownian motion is the square root of 2 dt, where d is the diffusion coefficient. And remember, what is Einstein's definition for d? Einstein's definition for d is this expression. Okay, last time we derived the diffusion equation following Einstein. Delta is the size of the jump. So this is a diagram, remember? Here. So delta is the size of a jump. That means if the initial position is x, and during a time period, a small time period tau, okay, there's going to be some physical assumption in regarding this tau, but let's just call tau a fixed time period, and in that period the displacement is random. The displacement is random and is denoted as delta. So this is x plus delta. Delta is delta denotes the displacement to the right. Okay, increase in the x coordinates. This is random. So basically, this integral without the 1/2 factor is the second moment. Is the second moment of delta, and we assume that delta is a symmetric random variable, so it has mean 0. So this is the, let's use a physicist notation for this, for the mean. That's delta square angle bracket. That's the mean of the delta square over 2 tau. This is the definition of the diffusion coefficient according to Einstein. And now here the square root of the displacement is the square root of the square of the displacement. No, the mean, okay, my goodness, I don't know how to say this. This is the root mean square, right? In electrical engineering, this is called the root mean square of x is the square root of 2 dt, which is a crucial result, which leads to stochastic calculus, because this result eventually will lead to the fact that Brownian motions is nowhere smooth, and therefore a stochastic calculus like Ito and Stratonovich calculus are needed. Okay, so this is the result given by Einstein, and Langevin managed to accomplish the same thing from a different approach. And this approach is much more physical, because there's actually going to be modeling of the forces that the Brownian particle experience. Remember, last time we also draw that picture. So this is the Brownian particle. Which is a pollen grain submerged in fluid, and the little particles, which are molecules, continuously bombarded at very high frequency. Okay, so that's the picture. And the little tau that showed up in Einstein's work is actually a very delicate parameter. Tau is a small time compared to the overall observation, the duration of the observation of a Brownian path, like something like this. Yeah, so this is, for example, the observed Brownian path over the observation period. Tau is very small compared to that period. However, it is much longer compared to the frequency that the particle, the fluid particle, bombards the pollen grain. So this is a very delicate time scale. It is small in a sense, and it's also large in a sense. Okay, so now let's come back to the actual physical process, which is the dynamics modeled by Newton's law, and that's the Langevin's approach. Okay, so this was a little bit of a review of what we did last time. So here, Langevin arrived at the same result for the mean square displacement at Einstein. Let's just write it on the side. Lambda x equals the square root of the mean of x squared, which is the square root of 2 dt. Big result. Also coming from a very different perspective and following, in his word, quote-unquote, infinitely simpler derivation. Interesting. Beginning with the trajectory of a single particle, his work marks the first attempt to provide a dynamical theory. Okay? So in mechanics, of course, we know the distinction between kinematics versus dynamics. Kinematics versus dynamics. So kinematics is the study of motion without studying its causes. That is simply to say, you're just going to record the trajectories, calculate the velocity, acceleration, that sort of thing. It's just the study of the trajectory itself over time. Whereas dynamics is, for example, Newton's second law is an example of a dynamical law. It tells us why particles move, right? There's a cause. Force is the cause, and the outcome is a trajectory. Acceleration is a direct outcome of a force, and acceleration accumulates over time, and so it gains velocity, and velocity accumulates over time. It becomes a a non-trivial displacement. So the dynamical theory of Brownian motion is proposed by Langevin, and here to be contrasted with Einstein's kinematical theory, which has nothing to do with the forces, right? Einstein only considered the displacement as a random variable, how it was going to say how is the displacement likely to be, right? Delta is the size of the displacement, the size of jump during time period tau. Okay, so what's the Langevin's argument then? Let's see. This is, by the way, the picture I used in the video in the thumbnail for the first live stream. Here, a single Brownian particle is subject to Newton's law of motion. So Brownian particle, remember, is a pollen grain. It is still considered macroscopic by classical mechanics standard. Okay, a Brownian particle is still too big for quantum mechanical effects to be noticeable. There's no need to use quantum mechanics for Brownian particle. Classical physics is okay. A single Brownian particle is subject to Newton's law of motion. The Brownian particle moves around because it is subject to a resultant force F coming from the collision with solvent molecules. Right? With enough information about F, Brownian motion can be studied using Newton's second law, F equals ma. So you have the differential equation m dx squared x over dt squared equals F. And physicists would probably write this as mx double dot equals F, where dot stands for time derivative, Newton's fluxion notation. Okay, hi everyone, thanks for joining the stream. So yeah, let's continue. The precise microscopic form of the force acting on the particle is unknown. Of course, F is very complicated. However, from a macroscopic point of view, it is reasonable to consider it as a resultant of two different forces. So first you have the viscous drag. This is a Stokes law in fluid mechanics. So for Stokes law to hold, you need several assumptions. So basically, the Stokes law says the drag force acts in a direction that is opposite to the velocity, so hence the minus sign, and dx dt, and is also proportional to speed. And gamma is the proportionality constant. This is a viscous drag formula according to Stokes. Okay, so it has its own range of validity. Okay, so basically it needs to have a low Renault number. The fluid has to have, it needs to be very sticky, and the speed needs to be slow. Okay, and we're just going to take this law for granted, and it's a useful first approximation. And gamma is 6 pi nu r. R is the radius of the sphere, of the Brownian particle, the pollen grain. And nu is the shear viscosity. So it's a degree of stickiness or friction in a fluid. Nu. Okay. So this is a viscous drag. So basically, you have this viscous drag that slows down the Brownian particle. But also there's the driving force, the fluctuating random driving force, FRT. R stands for random, due to the incessant molecular impact, about which next to nothing is known. Okay, so yeah, so that's the fundamental picture. The particles bombard the pollen grain. The fluid particles bombard the pollen grain, so it starts to move, but immediately it gets slowed down by the viscous drag. Okay, so that's the picture. So under this assumption, then we can write the equation of motion, Newton's second law, in the following way. Left-hand side is still ma. On the right-hand side, you have two terms. One is the viscous drag term, and another term is the random fluctuation force. So of course, if there's no noise, if there's no random term Fr, this is a well-known differential equation. Every student of physics, hang on a second, what's going on in my laundry room? Let me just leave for 10 seconds, I'll be back. Okay, all good. I saw a cat was doing some shenanigans, and obviously non-relativistic, of course, because the speed is very slow compared to the speed of light, and the mass is very small compared to something like a planet. There's no need for relativity either. Okay, so here we have this differential equation, and then this is an interesting arrangement, interesting manipulation. We're going to multiply x on both sides. Actually, let me just do the algebra here. So this is a physical picture, pollen grain with radius r, and it's been bombarded by fluid particles like this. And Langevin's equation Langevin's picture of Brownian motion says the following. Says m d square x over dx squared. Which book is this? It's in the description of the stream. It's the first link. It's Professor Matt Scott's book. Professor Matt Scott's note. Yeah. So go to the first link. There is a note at the bottom of that link. Actually, and you can go there. Okay. So this was explained in the first stream. So it's a physical introduction to stochastic processes. And it's very, so to say, it's very applied and not mathematically rigorous, but focused mostly on solution method and physical modeling. Okay, so the Langevin pictures of Brownian motion says the following. The right-hand side is a minus gamma dx over dt plus the random force Fr of t. Okay, and now we're going to perform a manipulation. That is, multiply x on both sides. We're going to multiply x on both sides. Multiply x on both sides. So you might wonder, why on earth would we do this? This is actually not so mysterious at all. First, let's write the multiplication. Mx, I will just use x double dot, okay, to save some writing. Minus gamma x times x dot plus x of Fr of t. Okay, of course, x is a function of t. Why do we do this? Well, the motivation for that is actually already clear from elementary mechanics. Recall from elementary mechanics. How do we derive the famous work-energy theorem? Work-energy theorem. So this is well known, right? So you have F equals ma, which is m, assume 1d, okay? To make things simple, m times dv over dt. Multiplying x has the advantage of getting rid of time dependence. So f times x equals m of dx squared over dt squared. F times x, this will, hang on a second, should it be x or, let's try f times x. F times x is m dv over dt times x. Or actually, it should multiply dx on both sides. My bad. The derivation of work energy theorem. Derivation works like this. So multiply dx on both sides. So the right hand side now read m dv over dt times dx. And then you just combine dx and dt to get v. So mv dv. And then you integrate to both sides. So f times dx. And now it's just the integral of mv dv. And by the power rule, this is just half mv squared, v final, v initial. So the right hand side is the change in the kinetic energy, delta Ke. On the left hand side is the integral of the force over distance, which is work. Right? So multiplying dx has this effect. And so we're going to do this similar trick, multiplying x on both sides. Not dx, but x on both sides. What is the advantage of doing that? So hopefully we can get something like this. We can get an mv squared term going on. Okay, so hang on. Here, let's see. This is x times x dot. This is half of d over dt x squared. Yeah, so this can be replaced by this. Okay, and what about the left hand side? What about this? So x times x double dot is, let's write it as, well, we want to connect this with x squared. We want to connect this with x squared, so let's write it as x times v dot, x times v dot, and perhaps use it like an integration by parts strategy. I'm not quite sure actually. So let's try to twice differentiate what happens when you say, let's twice differentiate d over dt squared times x squared. D squared over dt squared x squared. So see what happens. This is, of course, just d over dt of the first derivative. But the first derivative we already know here is 2 times x dot. This is the first derivative of x squared. This 2 times x dot. And from there, use the product rule. So you get 2 times x dot times x dot. And then plus, and plus 2 times x double dot. Yeah, so the x double dot is what we want, so you can isolate that. And the first term is 2v squared. So now you can write x times x double dot. Not super obvious, but and so yeah, it's not difficult to see. X times x double dot here is doing this rearrangement, and we get half d squared over dt squared of x squared minus v squared. Okay, and now let's substitute. Do the substitution. So the left hand side is now m over 2 d squared over dt squared x squared. Okay, and then minus mv squared equals the right hand side, which is minus gamma times 1/2 gamma over 2 d over dt x squared. And then finally times x times the force FRT. Okay. Okay, so yeah, this is of course the fundamental equation of motion. And here we arrive at this result after multiplying by x and some rearrangement. Okay. Now let's keep going. So here, this is I'll do the algebra on my note and read the commentary, the physics stuff with you guys on the PDF reader. Okay. Langevin remarks that since the quantity Fr of t has great irregularity, quote unquote. Okay, this is a very physical argument. So equation 1.17 is not a differential equation in the ordinary sense. So basically, this fluctuates with very high frequency due to the nature of the physical picture. Right? FRT has great irregularity, is a non-smooth function in time. It behaves like this, zigzag like crazy. In fact, since the forcing term Fr of t is a random function, so too will be the path x of t. And this is understandable because the driving force is random, the resulting x is also random. Okay. However, the path x of t is not Langevin's objective, right? Because imagine if you truly do solve this differential equation, if you do have the full information of Fr of t, and you actually do solve this differential equation, you get something like this. The best case scenario is that you will recover the trajectory, but it is a complete chaos. Like, what good does that do to you, right? So we're not interested in the trajectory per se, but rather its statistical quantities. So Langevin now performed another mathematical sleight of hand by taking the average. Oh, by the way, this is once again physicist notation for average. It drives statisticians crazy, I know, and probabilists crazy, but this is a notation in physics, which in my opinion is actually not that terrible, contrary to the opinion of statisticians, because it suggests that the average is an inner product, which it is. So anyway, this is just a notation for average in physics. Assuming equation 1.17, yeah, this one we just derived, has a well-defined meaning in a statistical sense, he proceeded to average the equation over a large number of similar but different particles in a Brownian motion under the same condition. So you may consider in the fluid there's a lot of Brownian particles, and each of them is described by this random differential equation, and then you can just take the average. Okay, so very audacious manipulation. So after taking the average, and we assume the average operator, okay, commute with the differential operator. So d square, the differential operator with respect to t, commute with the average operator. Okay, so this averaging is averaging all the trajectories. We're averaging all the possible trajectories. Assume this commute with the d over dt operator. Okay, once again, as I said, very audacious manipulation. Once again, this is something that drives statisticians and probabilists crazy. They will literally spend pages, if not a whole book, try to justify this. But yeah, physicists just do that in a heartbeat. Right? No remorse. And this is done. Okay, so now you have this new differential equation after taking the average over all possible trajectories, you get this differential equation. So now what? From the equipartition of energy theorem, this is a result in statistical mechanics. I mean, this series do not assume domain knowledge in statistical mechanics, but let's just use that. Okay, equipartition energy roughly says, okay, correct me if I'm wrong, because I'm not a professional physicist in chat. So it roughly says the total energy in on each degrees of freedom is the same. Okay, so from the equipartition of energy theorem derived in equilibrium statistical mechanics, Langevin was able to replace the average kinetic energy, this term. This is twice average kinetic energy, mv squared average by kbt. So basically this is the result in statistical mechanics. Let's just assume that. Where kb is Boltzmann's constant and T is the absolute temperature. Okay, so right now this is a constant term, which is a great simplification. And now you just have a differential equation for the mean of x squared. Right. So actually, there's also the random term. The cross correlation here. This is extremely audacious. It says Langevin says that the cross correlation, the mean of x. Remember, x is not an independent random variable to f r of t. Okay, x is a function of t itself. And we by no means assume that this is independent of FRT, but he just said, okay, this average is 0. This cross correlation is dismissed by Langevin, saying it can be set to 0 due to the great irregularity of FR of t. Can you imagine how furious a statistician will be by looking at this sentence? Okay, this is just 0. No proof, okay, just assumed to be 0. But then, well, miracles do happen sometime. So the resulting differential equation for the mean squared displacement, x squared, is then simply this differential equation. And this differential equation can now be solved analytically. Okay, we will do that in a second. And so later on, in the notes, Langevin's work, including 2 others, Ornstein and Ulenbeck, was criticized by statistician slash probabilist Doob, Joseph Doob. Doob was the founder of modern theory of martingales, a very important class of stochastic process fundamental to finance. So Doob and others formalized the theory of stochastic differential equation to formalize this sort of physical argument. Okay, how can you just cross them out? Okay, but now everything is heuristics. Okay, why can you interchange the order of operation? These are all brushed aside. Okay, so they just solve this differential equation here, and then take the average. Take average over all trajectories. So trajectories of the Brownian particle, you get this. So assume this operator commutes with d over dt, and you get m over 2 d square over dt square, the average of x squared, and minus mv squared average. Okay, just to be clear, I'm not making fun of physicists. Okay, just different priorities. If you have to stop every step, you have to perform an operation, no research can be done. So this is just different priorities, and it's totally okay. And if, let's say, I talked to a professor in quantum mechanics when I was an undergraduate. Oh, how can you just interchange operations freely? I say, okay, we do this on an active phase for sure, and whenever things go wrong, we check these assumptions. If it doesn't go wrong, we just assume it's okay, which in my opinion is with no remorse, okay, no remorse whatsoever, which in my opinion is totally legit, right? This is, after all, doing science is a community act. You do science to communicate with others, not to to explain data, to communicate with others, okay, not for pedantry. Okay, so now we have this average differential equation from physics, equilibrium statistical mechanics, from equilibrium statistical mechanics, and in particular the equipartition theorem. The average of the kinetic energy is kBT. Kb is Boltzmann constant, T is absolute temperature. And assume the cross correlation term x times FRT is 0. Let's put a question mark here. And let's put a question mark here as well. Okay. So this way we get a differential equation for x squared average as a function of t. So this way the differential equation, for x squared is as follows. Cross out this term and replace mv squared average by kBT. We get the following. So this is kBT, and move this to the right hand side, plus. Okay, so there's that. And what is this kind of differential equation? Well, this is a differential equation of it's a linear differential equation, right? M, gamma are both constant. So multiply 2 on both sides, we get the following. And let's also divide by m. Divide by m. All right, so this is the new differential equation. So to solve this, let's just for the sake of simplicity, let's write gamma over m to be a constant. So let's write that to be a. Why not? This is a constant. And 2 kb t over m to be little b. Okay, and now let's denote x squared average as a function of t to be, say, y of t. Let's say this is y of t. And y prime of t to be p of t. So we want to solve this differential equation. This differential equation, ordinary differential equation for x squared average is linear with constant coefficient. And by the way, a lot of people asked me what would be the prerequisite for studying this. I answered two things. It's just average. It's just the probability theory, basic probability theory. You know how to calculate the average and mean, variance, that kind of thing, as well as ordinary differential equation. Here we see this is the well-known ordinary differential equation from any introductory class. So doing this transformation allows us to write the differential equation as p prime, this is p prime or p dot, p dot, y dot. Let's use dot notation for the time derivative, because this is the second derivative of x squared, so which is just the first derivative taking time derivative. So this is just p dot equals minus a p plus b. And there are many ways to solve this. You can integrate it. You can do integration, separation of variables, and then integrate. Or here, because of the constant coefficient, you can also use a method called the method of undetermined coefficient. Use undetermined coefficient. Okay, this is pure differential equation stuff, which I assume the audience is well versed in. Okay, so the undetermined coefficient, it tells us that P is the solution pH, that's the solution to the homogeneous differential equation, namely without the B, and then plus PP, which is the particular solution. pH is immediately obtainable. pH is e to the minus AT times the constant C. So P dot equals minus AP. Solution is immediate, so that's just C times e to the AT. And because of the right-hand side, the inhomogeneous term B is a constant, so let's just assume the particular solution PP to be an unknown number, big A. So substitute into the differential equation. A dot is 0, and just minus A times big A plus what? Plus little b, which is just little b. Okay, no need to further simplify. Big A here we can see this is b over A. That's big A. That's big A. So therefore, together, the general solution for P would be C, as we call it C1. Okay, C1 e to the minus AT plus b over A. This is P. And what is P? Well, P is y dot. P is y dot. So therefore, you have x squared average, x squared average as the integral of P, because its derivative is P, and now that's solved. So just this integration, and the integration will give us, this is, hang on, you have C1 over minus A, which, well, is just another constant. By abusing notation, I just write C1. C1 e to the minus AT plus B over A, T, and then plus C2. Okay, so that's the differential equation, the general solution of the differential equation for average of x squared. Let's box that. This is quite important. And is there anything else we can use to get those constants? Well, first of all, at time equals 0, there's no movement. At t equals 0, the Brownian particles simply don't have time to move. So initial condition, x squared evaluated at 0 is just 0. And so as a result, so substitute t equals 0 into the formula, you get C1 e to the minus AT. The middle term, the linear term, cancels, and plus C2 equals 0. Oh, actually, e to the AT, e to the minus AT is 1. So C1 plus C2 is 0, therefore C2 is minus C1. Okay, C2 is minus C1, and as a result, x squared average is C1 e to the minus AT minus 1 plus b over AT. Plus b over AT. So, let's evaluate the constant. Okay, b over A. What is b over A? So these are physical constant. B is 2k here. B is 2kb big T over m. A is gamma over m. So this simplifies to 2kbt over gamma. All right. Yeah. So therefore, you can write the x squared average equals C1 times e to the minus AT. AT is A is gamma T over M minus 1, and then plus 2 kBT over gamma times little t. So this is what we get. Let's compare with the textbook. Right, so hold on a second. Hold on a second. Integrate once. Yeah, so the first derivative is this thing. Yeah, that's our p, right? Hold on, what is beta here? Is there a definition for beta? How come beta appears? C is a constant, omega is gamma over m. I thought this must, yeah, this has to be a typo. This has to be gamma. Okay, this has to be gamma. Beta did not appear earlier. Okay, so Langevin proceeded by noting that experimentally, omega is huge. Omega is huge, so he said, okay, so omega, so think about why is omega huge then? Omega is gamma over m. Gamma is the drag coefficient. Remember where gamma shows up. It's in the Stokes law. So the drag law says minus gamma dx over dt, right? So this is what gamma is. And m is just the mass of the pollen grain. Okay, so gamma over m, this is dimensionless. Oh, actually, it has a dimension. It has a dimension of a frequency, so that is the inverse of time. So experimentally, gamma is very, very large. Well, gamma is large means nothing, because to say a thing is large or small, you really need to look at the dimensionless variant of it. So here it says, so the exponential may be dropped after a time period about 10 to the minus s has elapsed. Okay, so because say t, the observation time t, is much greater than the reciprocal of omega. So that means throughout our observation time, this exponential term quickly decays to 0. So that's why he ignored this term as well. Okay, so you know what? I will redo this derivation. I mean, not redo, but simply start here. Okay, so let's write it here. So here you have, therefore, this is the same as d over dt of the x squared average is C1 e to the minus A is gamma over m times t, and then plus the b over a, which is 2kb t over gamma. Okay, here in the textbook there was a typo. It should be over gamma, not beta. Okay, so now this is the physics. So physics says omega over m is roughly 10 to the 8 hertz. So that is to say, for our observation duration, this exponential term is negligible. So for observable time scale, so this term can be dropped as well. C1 e to the minus gamma over m t, negligible. The statistician, mathematician, please hold your breath, okay? Now, strap your seatbelt. This is what they do in physics. So I was like my gut reaction would be, okay, what if C1 is large then? Right? So apparently this is how they do it in physics. They just nod along and follow, okay? So because after all, the result is what matters. Okay, so this is negligible, and as a result, okay, so you have d over dt, mean square, the mean square of x. This is just 2kbt over gamma. And then integrate, you don't need to worry about the exponential term. Okay, so it's just the linear growth. 2kb big T over gamma times little t. Okay, and no need for the rest. Oh, actually, you do need the initial condition. Okay, using the initial condition, x squared at time equals 0 is 0. Okay, so, and guess what? This is Einstein's relation. This is Einstein's relation because Einstein so did two things. Einstein, remember what we said last time, Einstein did two things. Here, Einstein derived D in two forms. First, Einstein also used statistical mechanics to express D as follows. So this is exactly kb T over gamma. This is kb T over gamma. And now what we have, so this is just 2D times T, where D is kbt over gamma. So Einstein derived the diffusion equation, diffusion coefficient, first just from the kinetic theory, or statistical mechanics, and then derived the diffusion equation, the PDE. Right? It turns out the solutions are Gaussian, and the standard deviation of the Gaussian is the square root of 2 dt. And Langevin derived the same result using this approach, with some very audacious manipulation. So that's interesting, right? So therefore, this is the final result from Langevin's approach. Okay, let's continue. So here, nu is the shear viscosity of the suspending liquid, and T is the absolute temperature, Kb is the Boltzmann constant. Yeah, we all know that. The unit Kb are such that Kbt has a unit of energy. Yeah, this is already know from statistical mechanics. Knowledge of the value of Kb is equivalent to the knowledge of Avogadro's number. Once again, another physics fact. Hence, of molecular size. Notice how the qualitative aspect of Brownian motion, item 4 to 6 from the table, page 3, are reflected in expression for the diffusion coefficient. So, yeah, basically, this is something we did last time. So, purely empirically, Brownian motion is shown to have these characteristics. As the viscosity decreases, the motion becomes more active. So nu decrease, d increase. Right? Remember, the d formula is kbt over nu. And the radius decrease, r decrease, not over nu, but rather over gamma. Sorry, gamma is 6 pi nu big R. Okay, r decrease, d should also increase. And lastly, t increase, d should increase. So these are all consistent observations to the formula here. Okay, so far so good. And now come back Of course, this is highly interesting, right? It's a completely different approach compared to Einstein. Einstein said nothing about the dynamics. Okay, so hold on a second. Did we already seen this? Oh, yeah, actually here. This is where we should be going. So you have this result, final result. The change in the mean square in x is proportional in time, consistent with the random walk. It should be clear from Langevin's equation that the stochastic process affords a tremendous simplification of the governing model. Instead of here actually there's an explanation of the equipartition theorem. Okay, the equipartition theorem, which allows us to replace the average of mv squared by kbt, is explained by this footnote. It says the equipartition of energy theorem comes from the classical statistical mechanics. In the absence of quantum effects, it states that at thermal equilibrium, energy is shared equally among all forms and all degrees of freedom. For an ideal gas, the average kinetic energy in a thermal equilibrium of each molecule is 3/2 kBt. And because in ideal gas, you just assume there's free movement of the gas molecule in 3 dimensions, and there's no potential energy, and potential energy is treated as negligible. So in total, the energy is 3/2 kBt. So we can say on each direction, the average kinetic energy is 1/2 kBt. This is 1/2 kBt. So and the kinetic energy is 1/2 mv squared. So mv squared average is kBt. So this is the result used by Langevin. Okay. Anyway, let's continue. So instead of inducing 10 to the 23rd auxiliary variables describing the movement of the solvent molecules, Langevin included their effect as a single random forcing function. Indeed, right? Because if you were to discuss the details of FR, then you have to include the collision of each molecule, which will be intractable, of course. So we just collect them into a single term called a random forcing term and treat it as a stochastic, basically due to our own ignorance. Lead to the Coase equation for the particle position xt, quoting Van Kampen. And actually, this he is the author of another reference. It's also a link in the description. He's written a text called Stochastic Processes in Chemistry, in Physics and Chemistry, another classic in the field. So go check it out. Together with the surrounding fluid, the Brownian particle constitutes a closed isolated system. Right? So what do we mean? Right? So a closed isolated system is like a differential equation that is decoupled. Right? So because in general, rigorously speaking, physically rigorously speaking, right, to describe such a system, you need an equation of motion for the pollen grain and also for the solvent particles. And of course, together they form a closed system. But then you get a differential equation with 10 to the 23 degrees of freedom. Right? But now we're just going to isolate the Brownian particle. So this way, the differential equation for the pollen grain is now decoupled, and it becomes a closed system. This is what it means. Okay, so now you have a closed system. The relevant variable x is the position of the particle, which constitutes a stochastic process. This is due to the fact that the single variable x does not really obey a closed differential equation exactly, right? Because it's supposed to, strictly speaking, it's supposed to be just one degrees of freedom among 10 to the 23rd. But this is what we care about. And interact with a host of fluid molecules. These variables are not visible in the equation for x, but their effect shows up in the random Langevin force. Fluctuation in x are constantly being generated by the collisions. Notice in retrospect the similarity between phi of delta. So phi of delta, earlier in our review, phi of delta is the probability distribution of the jump. in Einstein's derivation, phi is the density for the jump, because phi it satisfies the here phi satisfies the normalization condition for the density, and also we only assume small jump is possible during tau, as well as the moment condition, second moment condition. So here the randomness is captured by the size of the jump, right, delta. The size of the jump of the Brownian particle itself is modeled by this phi function. Whereas in Langevin's approach, the cause of the motion is assumed to be random, right? The cause of the motion, the random kicks are directly modeled as the random forcing term Fr of t. So it's a different approach. The similarity between Einstein's phi of delta and Fr of t of Langevin both characterizes fluctuations. Nevertheless, while phi of delta describes the effect of the force, right, the resulting jump, that's the effect of the force imparted by the collision, a kinematic approach. Fr of t treats the force itself as a random variable, a dynamic approach. As a result, Einstein derives a PDE governing the entire probability distribution, whereas Langevin derives an ODE for the first two moments of the distribution. Okay, so yeah, just to quickly go over what we just did, right? The stochastic process X satisfies the ordinary differential equation in a highly generalized sense, right? Because this is not a regular ordinary differential equation. And then by taking the average, we get a classical ODE for the moment, the average of x squared. And then with some additional physical assumptions and integration, you get the final result consistent with Einstein's. So these are two different approaches, but they must be connected somehow, right? Several critical remarks can be made regarding Langevin's derivation, and criticism were not long in coming. Well, we made several criticisms ourselves, right? What precisely is the function Fr of t? So the random forcing function is unclear. We know what the random variable is, and we know what a function is, but what is a random function? What is the mathematical meaning of that statement? So this requires a formalization of the notion of stochastic processes. Right? And if Fr of t is a random function, then x of t should inherit some of its randomness, right? Because x of t is an effect, right, of the cause Fr of t. So x of t should also be random. And we assume x of t obeys the differential equation. But how do we even know, right, the derivatives dx dt, d squared x over dx squared t even exist? And indeed, mathematically speaking, as we shall see later, they don't. Okay, the derivative of x does not exist. The trajectory is nowhere differentiable. So in a sense, the mathematics is nonsense. But somehow miraculously we get the right result. So this means this calls for an extension of ordinary calculus, aka stochastic calculus. What kind of averaging are we using, right? What kind of averaging? So I said something about the average, that is averaging over all possible trajectory. Of course, this is only helped the situation a little bit, right? This from 1.17 here, from 1.17 to 1.18. What sort of average are we talking about? Right? I said it is averaging over all possible trajectory, but how on earth this is actually done? Once again, it's unclear. So what kind of average are we using? Are we picking some a priori probability distribution and computing the expectation? If so, how do you choose the probability distribution, right? So you're talking about, when I said we're averaging over possible trajectories, we're actually talking about a distribution over the space of trajectory of x of t. This is beyond the capability of ordinary probability theory, right? In elementary probability, we only talk about the expectation of a random variable, scalar or even vector valued random variable. But how do you describe a probability measure over trajectories? It's a highly non-trivial concept. Are we taking an arithmetic average? So it's just the quote-unquote average. Right? This sort of questions very much drives the statistician and probabilist not very happy. Okay, so now setting the exponential term to 0 is also interesting, right? So how can we set that to 0? We're setting to 0 because omega is large and t is large. T is large in the sense that, the observable time scale is large. So what is going on over a very short time scale? It raises another question. Soon after 1908, paper by Langevin, several outstanding contributions to the theory of Brownian motion appeared. Of particular interest is these two fellows, Leonard Ornstein and George Ulenbeck. So here, actually, I want to show you guys a very interesting painting in Utrecht. Utrecht, I believe, is in Dutch. Is in Netherlands, right? Utrecht. My geography is not the best, but basically, here you have a painting at the University of Utrecht, or Utrecht University. And here it says, I believe, Professor Ornstein investigate random walk. And here, if you zoom in closely, there is a stochastic differential equation. By the way, this is the modern notation of stochastic differential equation. Notice how there is no dxt over dt, but rather just dx of t on its own. This is to avoid saying x of t has a derivative. Okay. Yeah, no worries. It's kind of difficult for me to nowadays, especially during weekdays, in a sense also weekends as well. I'm only truly free on Saturday, so I kind of have to squeeze streams during the day. I apologize if the time isn't the most convenient for viewers. So, but anyway, the recordings are there. Chat has been quite quiet. Maybe I've just been talking to myself. And any questions so far? Anything we've done? Perhaps I already anticipated the questions, like the questionable manipulations being done. Just any question is very much welcome. Okay, so this is not a lecture. I'm not a prof anyway. So this is supposed to be, for the most part, okay, this is supposed to be me reviewing stuff and taking it all. Okay, so this is supposed to be me reviewing this stuff and at the same time thinking out loud, just in case somebody find it helpful. I decide to record those sessions. Gamma moment threw me off. What is gamma? Gamma, you mean gamma function or gamma distribution? You mean these average process? Yeah, so each step is really very ingenious. Like, the first equation, let's chat, let's do a ranking, so to say. In terms of audaciousness, which step, or audaciousness / ingenuity, which step is the most ingenious in your opinion? First of all, multiplying x on both sides is pretty, it seems pretty, I would say, it's ingenious. But perhaps from a physicist's point of view, this is to be expected, right? Because you want to connect this with energy. And this is how you derive the work energy theorem. So I was trying to motivate this step, multiplying x. Right? So I was trying to motivate this step. So this is by no means a trivial step. Okay, the manipulation is routine, but having this idea is not trivial. And this allows us to connect with kinetic energy, mv squared. So you can, and now you take the average, quote unquote. After you can take the average, you can apply the equipartition theorem. So the differential equation for the average of x squared is now manageable. And after we've done that, dropping the exponential term. So how many miraculous steps are we dealing with here? Almost every step, right? 1.11, 1.18. 1.11 is multiply x. 1.18 is taking the average. Okay, and then 1.19, yeah, 1.19 is dropping the cross term. I forgot to mention that this is also highly non-trivial. Why is that true? Simply due to the great irregularity of FR. Wow. And finally, dropping the exponential term. Dropping the exponential term, I mean, e to the minus omega t might be small, but how do you know that c is also small, right? So it's 1.20. So these are all, ignore the exponential term. Set the e to the c times e to the omega t to 0. Which step is, in your opinion, the most, how should I say, questionable, or yeah, you can't argue with the result. The result is correct. It's physically verifiable, but the process is quite interesting. Anyway, yeah, think about that. Physical intuition can be extremely non-trivial as well as making a good guess. Exactly, exactly. Physical intuition is, you have to, this is sometimes, you know, the thing is, you know, don't taking this as me making fun of physicists, because as a matter of fact, not opinion, okay, most great mathematics come from physics. So it's impossible to get everything rigorous at the first investigation, right? Yeah. So I'm not sure if you guys are aware of this, but this kind of reminds me of a parallel situation. There's this field in probability theory that originated from statistical mechanics called spin glass. Has anyone heard of this field called spin glass? This is perhaps a hidden gem, but a hidden gem in probability theory. It comes from statistical mechanics in condensed matter physics. So spin glass physically is a magnetic state characterized by randomness. So it physically it's meant to describe the magnetic property of certain alloys. It's a spin glass. And there are various models to explain it, that explain this, the phase transition. So you have the Edward Addison EA model, and as well as SK model, Sherrington-Kirkpatrick model. And so basically what happened is physicists, in the process of trying to find solution of the SK model, invented a trick. Invented a trick that's, mathematically speaking, nothing short of a miracle. So this is called the Parisi solution. Italian theoretical physicists. And mathematicians later spent years to justify Parisi's method, in particular Michel Talleyrand. Michel Talleyrand is a French probabilist. So he did work in functional analysis, probability, and mathematical physics. One of his greatest contributions was to justify the step. I mean, I don't pretend to understand it, okay, but I'll be completely honest. I initially tried to gain a PhD position in this field, but I was rejected. So I decided, okay, this is the end of my academia career. Okay, But initially, in my graduate school years, I was very much intrigued by this field. So Talleyrand's proof of the validity of Parisi's formula. Okay, so anyway, the point is, in physics, often quote-unquote nonsensical manipulations are made first with great practical success, and then mathematicians try to scramble to catch up with how to justify things appropriately. Of course, this is not a scandal by any means. This is how science progresses. Right? You discover a method that works in certain situation that the current theory fails to explain, right? And then theory catch up. Sometimes theory proceed farther, so than practice as well. This happens all the time. You see what I'm trying to say. Okay, chat says I already got lost when I see physicists doing df times dg dx and canceling out stuff. Yeah, exactly. I did that too. Right here, I did that too. So I just say, combine dx and dt instead of dv and dt. Right. So basically, what you're saying, casual polemics, what you're saying is treating derivatives as a fraction in chain rule. Right. In general, the derivative notation, the Leibniz notation, cannot be treated as fraction, but in certain situations, it's okay. In the chain rule, in what's that? The U substitution, which is essentially chain rule, this is okay. It can be mathematically justified, but when you do apply science, you manipulate infinitesimals all the time. But of course, in pure mathematics, you have to actually define what is dx, things like that. You can treat dx as a linear functional. You can treat dx as what we call infinitesimal in non-standard analysis. But we just don't have time for that right now. Okay, we're too busy with doing physics. Okay, let's continue. Okay, what about Ornstein-Ulenbeck? We'll see that today. Okay, we'll see that in a bit. By the way, I haven't still finished showing this this website. It's in the stream description. It's a website run by Utrecht University. Here, this mural painting shows the drunkards wore random walk. As an example of random walk, Professor Leonard Ornstein investigated. You can visit this mural at this street. I don't speak Dutch, so the random walk is a series of random consecutive steps an object can make. This theory is used to create models for predictions, like stock prices of how a floating object move across the water, like pollen grain. So in a nutshell, okay, this differential equation, this stochastic differential equation describes the velocity of the Brownian motion. Now, this is a velocity process of Brownian motion. And besides Brownian motion, it has also been applied in finance, in the modeling of interest rate. I believe it's called the Vasnik model. I don't know how to spell it, but Vasnik model. Is that how you spell it? Probably wrong. Okay, yeah, Vasnik model for interest rate. So mathematically speaking, it is the same as the velocity process of Brownian motion. We'll get to this stochastic differential equation soon. Okay, so yeah, it's used to model interest rate, stochastic investment model. Okay, I know a lot of you guys are interested in finance stuff, but right now we're doing stochastic process for a physicist, and then we'll rotate for finance, for engineering. There's going to be some overlaps, of course, because the fundamental mathematics, I wouldn't say it's the same. There are subtle differences, but largely we will, in the series, kind of repeat the same material. Not the same material, but the same core material, but with different emphasis. It's like in the university you have calculus for engineering, calculus for mathematician, and calculus for physicist. But unlike in university, where you can only take one, right? These are anti-requirement, right? For example, if you take the calculus from math, you can't count it. You can't retake or at least not count as credit, right? In the physics department, then retake the calculus or physics department, right? But here you can watch whichever episode you like. So, yeah. So because yesterday I just had a nice conversation with a fella in my Discord server. He is actually a grad student in physics department. He works in atmospheric physics, cloud physics. And he showed me a course he intended to take from the math department on stochastic process. I was looking at it, I was like, this is pretty much has nothing to do with physics. And later on, he said his advisor agreed with my opinion. That's kind of it. So instead, right now, he's going to take the statistical mechanics course from the physics department. There is a wide gulf in literature in stochastic process. Stochastic process is so useful that different groups of people develop different tools, sometimes equivalent tools, different notations, different emphasis. It's kind of hard for beginners to see what he or she exactly need. So there's that. The situation kind of parallels the scenario in tensor calculus. So chat says physicists generally take the ask for forgiveness before permission approach. Although it doesn't always work out, but when it does, you hear about it. Exactly. So it's extremely rigorous physics tests, physics textbooks such as Landau and Lifshitz do what we just saw all the time, and they're considered rigorous because the emphasis is different. Right? In physics, tracking down mathematical detail does not mean rigorous. What's important is what physical assumption is being made, and how does the mathematics reflect and predicts it. Okay, and it's interesting because this morning I got a comment here. I was saying that the situation in stochastic processes in different fields very much parallels the situation with differential geometry and tensor calculus. So I'm currently still also have an ongoing series of tensor calculus. We're trying to get to the notion of Riemann curvature tensor. And under the latest episode, which is covariant derivative, I received a comment. Here, I will just show you guys. This morning, here, covariant derivative.
Let's get started.
Okay.
So
this is a stream recording for covariant derivative. And see what we have here. There's a comment. It says here, let me zoom in this way. It says, thanks for the video, but the tensorial notation is always a mess. He or she is referring to a precise moment where I derived give the formula for the general, right here. It's in this big box right here. Still haven't finished writing that down. It took me several minutes, something like 5 minutes to write down the formula itself. Here. This is the general formula for the covariant derivative. Looks absolutely horrendous. And I do concede, although there's a nice pattern to it. Okay? And I do concede on that. And here's what he says. Thanks for the video, but the tensorial notation is always a mess. No one, quote unquote, I don't know why, no one remembers that after a few months, if one is not practicing tensorial notation day in, day out. The interpretation of a result in tensorial notation is still more intriguing. Yet programming that is easy. There are better ways, one without index shuffling. The same S is done now since more than 100 years. to show the origin of the covariant derivative. What are you showing here is standard stuff in thousands of textbooks. Why are you showing us that once more how to do it the wrong way, quote unquote, one that led students despair? And here's my reply. Because students of physics and engineering need to read textbooks and papers, like you mentioned. We'll do the index-free way later. You see, notations reflect the history as well as priorities of discipline. Notations, conventions of rigor, because, come on, every mathematician talk about mathematical rigor, but no one can define it, right? So there's no objective standard for rigor. It's a field-dependent thing, as well as what is quote-unquote elegant notation, right? So the thing is, in applied sciences, we work with coordinate system all the time, right? Let's say if you define, in general relativity, if you define tensors abstractly, then you have to do the extra translation into coordinate system. Of course, it works, but the physicists feel that the tensorial notations are more straightforward. So there is that. And as applied mathematician, we need to be bilingual, because the primary objective of applied mathematician is not to prove new theorem, although that can still happen, is to promote scientific communication. That is to say, we take the advancement in pure mathematics into applied sciences so that applied scientists can have a more accurate and more efficient way for modeling and prediction. And at the same time, applied sciences provides raw material for mathematical research, because stochastic calculus would not even exist without Langevin's audacious manipulation, right? And as well as the Parisi solution in spin glass. Much of pure mathematics would not even exist without quote-unquote questionable manipulations. So that's the thing. So as applied mathematician, we need to be bilingual. So that's why I said we will do the index-free notation later. Don't you worry. Right. So that's basically my stance on the subject. Of course, you can always promote your own preferred approaches. Like it happens all the time. Like, for example, in the late 19th century, there's dispute over which is superior, vector calculus, vector analysis, vector calculus, or quaternion. History turned out to favor vector calculus, and quaternion is now in relative obscurity. And this is just what happened. Whichever tool that suits the need of scientists the most tend to survive. Okay, anyway, this is foreshadowing what Ornstein and Ulenbeck did, and we'll come back to this particular website, okay, on this mural painting later, because it actually has a nice explanation. This is not just a tourist website, okay? Actually, there's a nice explanation. Who was Ornstein? What did Ornstein do in Utrecht? What did he discover? How did he discover this? What does the formula mean? Yeah, there's actually explanation. Actual math, okay? Going on the tourist website. Pretty cool. What does random walk look like? Oops, cannot load. Fine. Read more. Further explanation. So cool. I wish more websites have this. How awesome is that? Anyway, go back to Professor Scott's note. Relation between Langevin's approach and the rest of the course. Random differential equation, or aka stochastic differential equation. Langevin's formulation of stochastic process in terms of Newton's law of motion still appeals to many physicists, because you can describe the dynamics directly. Right? Unlike Einstein's approach, right? Einstein's approach to derive the PDE is not as direct as describing the force in a straightforward manner. For systems governed by linear dynamics, In the absence of fluctuations, Langevin's approach is very intuitive and simple to formulate. Right, so why this is important? Remember, this key manipulation we did here, multiplying x on both sides so that you can create a time derivative of x squared. This is only possible because of the linearity, equation 1.16. So this was only possible due to linearity. Right. For a nonlinear system, this ingenious trick no longer works. For nonlinear system, however, Langevin's approach cannot be used. Differential equations with stochastic forcing or stochastic coefficient are the subject of chapter 8. And by the way, this is also the subject of this upcoming Saturday's live stream to be scheduled, because I have not yet created the live, oh, no worries. Yeah, these sessions are long, and I don't expect anyone to watch from start to finish. But I hope this is still helpful in some way. So as I was saying, this is also the subject matter of this upcoming Saturday's live stream, Saturday morning's live stream, Introduction to Stochastic Differential Equation for Applied Scientists. This is what we're going to do, and eventually we will, hopefully not too long, we will see how stochastic differential equation interacts and synergizes with the partial differential equation, which we also have an ongoing series. So far we are at first order partial differential equation, and the next, after we finish that, it's pretty soon, after that we will do heat equation. And heat equation, of course, we already seen, right? Heat equation, diffusion equations, it's already seen earlier, right? Derived by Einstein. And eventually the two will be connected beautifully through what we call the Feynman-Katz formula. Feynman, how do you spell? Yeah, is that how you spell Feynman? Feynman-Katz formula. So this is the link between PDE and SDE. You have a PDE, the solution can be written as expected value of SDE, this theorem. Pretty awesome. Okay, so this is actually one of the goals of the stochastic DE theories, to arrive at this formula. I mean, not going to prove it fully rigorously, because the series is meant to be aim at an elementary level. After all, only assume differential equation and probability, no measure theory. So this is not going to be a fully rigorous proof, but we will get the idea for that. Okay, and it's used in, for example, mathematical finance. You can use it to derive the derive the Black-Scholes formula. Okay. Anyway, there's that. Let's come back here. The difficulties of Langevin's approach for a nonlinear equation is discussed in Van Kampen's also Dutch article, Fluctuations in Nonlinear Systems. I believe this article is on Professor Matt Scott's website. Okay, guys, let me open the link for Professor Matt Scott's website. Yeah, so this is Professor Matt Scott's homepage. The notes is here, the final link. Is this one? No, actually, no, not this one. Review article Fluctuations by, this gotta be this one, right? Fluctuations in nonlinear system. Or just fluctuation. Come on, please load. Oh, actually, this is a very nice tutorial paper. We could have just used this, but it's much harder to read, of course. It's much shorter. But a lot of the same thing will be completed in Professor Scott's note. Okay, this is a great paper. But not the same as the one mentioned in the notes, huh? Not the same. Okay, but nevertheless, this is a great paper. Was reading something about this theorem. I have no idea what that is. Basically saying with Markovian process, they must be expressed as a sum of the first and second derivatives and an integral. That's therefore non-local effect. Okay, interesting. Actually, you know what? I'll put this down in my notes because I have no idea what you're talking about. I have to look into it. What is this theorem? It was very interesting. Okay. Yeah, definitely. I'm intrigued. I have no idea. You see, I learn a lot from my viewers. Is this one you're talking about? No, this is with Ramsey's theory, not the stochastic process. Ah. Characterize the infinitesimal generators of Feller semigroups. More generally, Levy-type operators in probability and functional analysis. But you know, semigroups and stuff are very much related to the Markov process and things like that. Okay, excellent. Okay, excellent. Very deep, huh? Very deep. Yeah, we established thinking formula and CVW theorem for sublinear Markov semigroups. Is this one you're talking about? Chat, casual polemic? This is very similar, right? Oh, excellent. Thinking formula. Okay, you know what? Let me download that paper. Okay, but I'm not going to read it right now. Okay, and stochastic analysis, the Cavalier treatment of the analytic properties of the random force, FRT, and the resulting analytic properties of the stochastic process, X of t, generated extensive activity by mathematicians to solidify the foundation of stochastic calculus. Particularly note is the work of Kolmogorov, Dubh, and Ito. And also, perhaps unsung heroes, okay? Unsung heroes deserve to be mentioned is the Ukrainian school of stochastic process. Okay, so actually, I mean, I guess due to the Cold War and stuff, Ukrainians, the Ukrainian school of probability and stochastic process developed an alternative approach to Ito's. I mean, I wouldn't say alternative because actually I'm not quite familiar with their details of their approach, but independently, definitely. Okay, so and their work is in, for example, Skorokhod, Anatoly Skorokhod. So he was a representative of the Ukrainian school of probability and statistics, and in particular stochastic process. So Skorokhod has written, and as well as Gichmann, together they wrote, I believe, 3-volume treatise of stochastic process, of general stochastic processes. So definitely, so basically they kind of developed the stochastic calculus independently than in the West compared to the West. There's different differences between their approaches. That's what I heard, but I didn't have the opportunity to learn this in detail. And there's actually a YouTube channel run by representatives of the Ukrainian school, current Ukrainian school. Let me try to find it here. It's a YouTube channel called Stochastic Process. It's called just theory of stochastic process, I believe. Criminally undersubscribed, only a few thousand subscribers. So theory of stochastic process, I believe. It was described in chat with AI links to a French paper, but basically said under right assumption on the past behavior, infinitesimal generator for Markovian processes of the form. Okay. I'll continue. I'll let you continue write your message. This is fascinating. There should be, yes, there is a channel called the theory of stochastic process. I'll put it in chat. Criminally, absolutely criminally undersubscribed. Is run by the Ukrainian school. It says the Department of the Theory of Случайных Processов Institute, and they're still using Russian. Okay, but yeah, this is the Ukrainian school, and it's, for example, let's just check out their stuff. They have their courses, mini course stochastic semigroups, lecture course large deviation, introduction to SDs and numerical method for SDs. This is a gold mine for stochastic analysis. Gaussian measure, you know, crazy stuff. You got these 4 courses in English, by the way. I mean, also in Russian. This is in English and Russian. Okay, let me share that channel in chat. But of course, you do need a measure theory background. This is research level math after all. Here. So much material, I know, right? Yeah, go check it out. This is the Ukrainian school of stochastic process. So yeah, actually, on this channel, we sometimes, and perhaps actually you can maybe even argue, often talk about Soviet-era mathematics. The Ukrainian schools deserve its own coverage, actually. So they have their distinct focus and sometimes approaches compared to, say, the Moscow State University in MGU. So there's that. Okay. So anyway, let's come back to the main topic here by Ornstein and Ulenbeck. So the Ornstein-Ulenbeck paper, which appeared 22 years after Langevin, begins by reminding the reader that the central result of both Einstein and Langevin is the mean square displacement. Okay, yeah, the central result is, oh, no worries, casual polemic. Thank you very much for your very thoughtful, and actually I was very pleased to find this new result. I mean, I'm perhaps not completely new in the research sense, but certainly new to me. Thank you very much for your contribution to the chat. Okay, so here, this is the central result. That's the average of x squared is linear in time, 2 dt. Einstein obtained the result. Gamma is the friction coefficient, this one, kinematically, from the evolution equation of the probability distribution. While many workers prefer Langevin's dynamical approach based on Newton's law. Right, so this is 2 different approaches, along with some natural assumptions about the statistical properties of the forcing function. Next, Ornstein and Ulenbeck go on to observe that the Brownian motion problem is still far from solved. Right, so Einstein and Langevin managed to explain the empirically verifiable law of the standard deviation. The standard deviation grows linearly in time. But this is still, there's a lot of more questions to be answered. Here, Einstein, Shmuluchowski, and Langevin all assumed a time scale, right, such that t is much greater than m over gamma. Remember here in Einstein, in these three people, in particular in the first two, Einstein and Smoluchowski discretized time. They have this time scale tau. Time scale tau is much smaller than the observable time scale, but is much greater than the microscopic time scale for the dynamics. The forces, the fluctuation of the forces is much shorter. The fluctuation period of the forces is much shorter than tau. So in each tau, the resulting motion is the accumulation of countless collision. So that's the assumption here. So we all assume the time scale t is much greater than m over gamma. Under what condition is this assumption justified? And what changes must be made to the formulation if the Brownian motion particle is subject to an external field? Because so far you just have two forces, right? Just have two forces. I mean two category of forces. One is the viscous drag, and the other is the random fluctuation. But what if there is another deterministic force imposed by, say, a force field, gravitational field, electromagnetic field, and so on? So how do you incorporate those effects into the random differential equation? Can you just add an extra term? Or what do you do? Right? So what changes must be made to the formulation if the Brownian motion is subject to an external field? The Ornstein-Ulenbeck paper is devoted to answering these outstanding questions. Their paper 2 is classic. We paraphrase below, although the reader is encouraged to seek out the original. Actually, the original paper by Einstein, by Langevin, and also here by Ornstein-Ulenbeck are also, they're all pretty readable when it comes to the mathematics. So here, the problem is to determine the probability that a free particle in a Brownian motion after the time t. Okay, the problem here is to determine the probability that a free particle in the Brownian motion after the time t has a velocity which lies between u and u plus du. So now we're calculating the probability. Brownian motion after time t, so we're talking about x dot of t, the velocity, probability between u and u plus du. So we're trying to calculate that. When it started at t equals 0 with velocity v naught, they declare their intention of using the Langevin's equation. So here in the Langevin's equation, this is the Langevin's equation. So you have du over dt plus beta u. Beta is, hold on a second. I saw this is big omega. Okay, anyway, a different notation. Fine. Perhaps this is because of the paraphrasing. Right? They use, perhaps due to the paraphrasing, Professor Scott uses the original notation. Du over dt, that's the acceleration. U is the velocity. Right? Du over dt plus the beta of t equals at. At is f of t over m. Right? So actually, let me derive this. Okay, so this is a well-known result in ordinary differential equation, but let's still derive this. Okay, here, Ornstein-Ulenbeck velocity process. of Brownian motion. So u is the velocity of Brownian particle. So following Langevin, we have the equation of motion. We have the equation of motion for u, which is du over dt plus beta of u plus beta times u equals big A of t. So beta is gamma over m, and big A is f of t over m. There you go. So that's the equation of motion. And the formula here, right, is the so-called variational parameter formula. And also we have the initial condition. Okay, initial condition is known. U when t equals 0 is u naught. So you can get the solution here. Let's just write the solution and then we'll write the derivation as well. Solution is u. This is purely formal, okay? Purely formal solution in the sense that the steps may not be mathematically justifiable. Purely formal solution. U naught times e to the minus beta t plus e to the minus beta t times integral from 0 to t e to the beta xi a of xi d xi. Okay. Well, how do you derive that? Well, this is a standard, the form at least, is a standard ordinary differential equation from a first course in ODE. You can use the integrating factor method or the variational parameter method. Both are equivalent. Derivation. This is standard ODE stuff. Let's use integrating factor method. The integrating factor method says first we calculate the integrating factor, which is e to the integral of the coefficient of u, here is just beta, and then dt. This is e to the beta t. We ignore the integration constant, that's not important. Multiply integrating factor on both sides, and we have du over dt e to the beta t plus beta e to the beta t times u equals e to the beta t times a of t. So on the left, assume regular calculus still works, which is a big if. Remember earlier I said that because of the Brownian scaling law, x equals square root of 2 dt, the stochastic process is nowhere differentiable. And as a result, regular calculus fail. But here we're using the regular calculus. That is to say, we're assuming the product rule still works. Assuming product rule still works, but here, the integrating factor step violates nothing. This is just ordinary calculus. Beta is a constant. So now assume calculus works, namely, in particular, the product rule works. The left-hand side is d over dt of u e to the beta t. Okay, and the right-hand side is e to the beta t at. Okay, so now we can integrate both sides. So on the right we have u e to the beta of t, e to the beta t, and then minus u naught. On the right hand side you get integral from 0 to t e to the beta t. You cannot use t anymore, so let's use xi, a of xi d xi. Okay, and now it's just a matter of rearrangement. You can get u equals u naught times e to the minus beta t plus e to the minus beta t times integral from 0 to t e to the beta xi a of xi and d xi. Okay, the derivation here is purely formal because we don't know whether the usual calculus rule is still valid. But this is a formal solution. Okay, let's continue. This is the solution. By solution, they mean an integration of the Langevin equation. Is that sensible, right? So the question is raised. I try to make that explicit by saying that we use the product rule in a process. We don't know whether this is okay, but let's first try that and see how things go. So on taking the average over the initial ensemble, once again, what does average mean, right? Initial ensemble making, it seems to suggest that you're considering a large ensemble of Brownian particles. You consider the individual velocity process and you just average over them. Okay, so here, once again, we assume interchangeability of operation. So taking the average here, okay, average over ensemble average. So you get the average of u is, well, the first term is a constant term, so it's non-stochastic, right? This is purely deterministic. U naught, unless you treat u naught as a random variable, which we don't, right, at the moment, e to the minus beta t. And then take, well, the average of e to the minus beta t, integral from 0 to t, e to the beta xi, a of xi, d xi. So now you interchange the order of integration and the average operator so that it now reads, okay, e to the minus beta t gets taken out, integral e to the t. E to the beta xi, this term is non-stochastic, so it gets taken out of the average operator, meaning this is the same for all particles, same time. And then a xi, d xi. Here we assume a xi is 0. A xi average is 0. Okay, once again, this is a physical assumption. The thing is, right, so you can consider, here this is your liquid, particles are in there doing their random walk thing. But because there's no net displacement, you can infer on average the forcing term is 0. On average, the forcing term is 0, so therefore the integral vanishes, you just get u naught e to the minus beta t. So this is the average of the velocity process. As you can see, the average tends to 0, regardless of the initial velocity. The average tends to 0. It doesn't mean the Brownian motion will grind to a halt. No, of course not. Or eventually still slow down. Remember, the motion is incessant. It never stops. It's just that even if you start from a non-zero initial velocity, eventually the average velocity over the ensemble will tend to 0. They cancel out. Doesn't mean they stop. It's just that after enough time, chaos kick in, and the velocity, they all become random. They cancel out. They're still non-zero. They never tend to 0 individually, but the average tend to 0. Okay, so this is what it means. So it's kind of important result. Let's rewrite that and box it. So there you go. The average of the velocity process. This is in contrast to the average of the position in Brownian motion. In the Brownian motion, earlier, last time, you have the Gaussian distribution as a solution. So the displacement on average is always 0 for all time, whereas the velocity will tend to 0. Okay, so that's the prediction of the model. Okay, so the subscript meaning average of all u that begin with velocity u naught at time t equals 0. So this is essentially a conditional expectation. This is a conditional expectation. So one of the criticism by statistician on physicist average notation is that how do you write conditional expectation? And here's how they do it. Of course, we know in statistics you write conditional expectation this way, or simply x given y. Well, physicists just add a subscript. You're conditioning on velocity being given equals u naught. Okay, so and here's what's interesting. We're going to square the solution and then take the average. So think about what we're trying to do here. We're interested in the, it's kind of like we're interested in the mean square displacement. Here we're interested in the mean square velocity. Okay, so let's do that. Here, let me actually add u naught here. Conditioning on the initial velocity being u naught is this thing. Okay, so now let's square the solution. And then take the average. Here. So our new objective is the average of u squared. So this is u squared starting with u naught. Okay. So this is our u, and then you square it like this. Okay, let's see what we have here. U naught squared e to the minus 2 beta t, and then plus 2 u naught e to the minus 2 beta t, integral 0 to t. This is the first order term. Okay, and then the second order term e to the minus 2 beta t, the integral square. So the integral square can be written as a, you can change the dummy index, right? So you can change the dummy index to what is the choice here, eta. Okay, nice. So let's say this is the integral from 0 to t e to the beta eta, a of eta. Oh, yeah, eta. 然后let's first write xi. And then d xi, integral from 0 to t e to the, oh, here, the first one is xi. You just change the dummy variables, okay? Nothing is actually changed. Beta eta times a of eta times d eta. Okay. So the integral can be combined into a double integral. 0 to t, 0 to t, e to the beta xi plus eta, a of xi times a of eta, d xi d eta. To combine the product of two integrals into a double integral. Okay, so it seems like that's what it does. Right. And then you take the average, the first order term cancels, of course, just like earlier. u squared, taking the conditional expectation of u squared, assuming u naught is a constant, you get u naught squared e to the 2 minus beta t. The middle term cancels, and here the second order term is e to the minus 2 beta t, double integral both from 0 to t, e to the beta of xi plus eta, and then you take the average of a of xi, a of eta. Here I'm omitting the subscript u naught here, because you can assume that the forcing function a is independent of the velocity, initial velocity. Okay, so initial velocity is not affected by the forcing function, so the conditional expectation just becomes regular expectation. Okay, so that's the result. And so all attention is now focused on this thing, the average of a of xi times a of eta. And this is a correlation function. Of a of t. So let's continue. Here, to make progress, now we assume that the correlation function has this form. So this is interesting. So we assume that the correlation function, the correlation between two random forcing terms, depends only on their time difference. That's the key assumption here. Okay, in the language of a stochastic process or time series analysis, we call this kind of process weakly stationary. The correlation is, not the full definition, but a feature of a stationary process, weakly stationary process. The covariance function or the correlation function, actually it should be covariance function. Oh, it's called a correlation function. In stats, they call it the covariance function. Here they call it correlation function, which again, this introduces extra confusion, right? So in stats, you actually have to normalize the covariance function to get the correlation, but here they call it the correlation. Basically, we assume this is a stationary process, as mentioned, and also this phi has this property. This phi is close to 0 everywhere except at the origin where it has a very sharp peak. What does that mean? It's a delta. So phi is very close to delta. That is to say, the forcing term the correlation can only be felt if the two time instances are close. So A quickly forgets its history. Basically, this is what it means. So phi1 is a function whose value is close to 0 everywhere except at the origin, where it has a very sharp peak. Physically, this is justifiable on the ground that the fluctuating function a of t has values that are correlated only through very short time instance. So once again, this is a delicate issue, right? Because earlier when we discussed the position process, that is, according to Einstein, Smoluchowski, and Langevin, we also talk about quote-unquote small time. Is this the same small time as we had earlier? Remember, what is the time scale earlier? The time scale tau, I'll use Einstein's exact word, well, translated of course, going back to Einstein's paper. What is tau? We introduce a time interval tau into consideration, which is very small compared to observable time intervals, but nevertheless so large that in two successive time intervals, tau, the motion executed by the particle, can be thought of as events which are independent of each other. So going back to the picture, right? So this is the full trajectory. Over a time period tau, say the particle only moves by this some small amount. And this is the consecutive time interval. Tau is small compared to the overall observable length scale, but it's still large enough that these two can be treated as independent. Why can you treat them as independent? Because over each period, the position change is a result of a very large number of collision. So that's the basis, the physical basis, the physical meaning of tau. Is this the same time scale in analysis by Ornstein Ulenbeck? Remember, here we're modeling what? We're modeling the forcing term. We're modeling the forcing term, the correlation of forcing term. So that is to say, going back to this picture, the forcing term AT per mass is a vectorial sum of forces exerted by the solvent particles whose numbers are around the scale of 10 to the 23rd. The time scale is now the fluctuation in AT itself, right? Not the time scale based on the trajectory of the pollen grain. So here, by a very short time, the very short time is still much larger than the frequency of A of t. This quote-unquote very short time, here, let me reread this again. A of t has values that are correlated only through very short time instants. So it's like the impact time of a particle. So strictly speaking, if you consider the impact is felt at a particular time and it's immediately not felt, right? Immediately is already the force is you touch, right? The particle touches the pollen grain at one instance after extremely small period. It's then forgotten. So basically, here, this very short time instant is still larger than the collision frequency. That's what I'm trying to say. As we'll see in the coming chapters, phi 1 is called the correlation function or autocorrelation function of A of t. The dependence on time difference only, T1 minus T2, is a typical of a special class of stochastic process. That's stationary process. So you're assuming AT is stationary. Okay, let's write those down. So assume A of xi, A of eta, okay, is a function of xi minus eta only. Let's call it phi 1. Okay, phi 1. So this is stationarity assumption. And also the shape of phi is like this. This is phi of t. Is like this. So we're assuming that the parameter t is chosen at a scale that is still much larger than the period, the fluctuation period in the forcing function. Okay, so there's that. Okay, in Ornstein and Ulenbeck's own words, we will naturally make the following assumptions. There will be correlation between the values of the random forcing function A of t at different time t1 and t2 only when the absolute value of t1 minus t2 is very small. So why am I spending time on this? Because when it comes to modeling, you have to decide what kind of time scale you choose for your problem and whether various assumptions actually hold. For example, in financial application, let's say A of t is, in financial application, you can also have this sort of differential equation to model interest rate. So A of t is supposed to be unpredictable factors that affects the interest rate. For example, on what ground can you assume that the random factors that influence the interest rate behaves in a similar way? So you should choose t to be in, say, in weeks, years, or what? Right? The mathematics itself does not tell you that. You have to make that decision. So this is why I spend time on this. At different time t1 and t2 only when the absolute value of t1 minus t2 absolute value is very small. More explicitly, we shall suppose that, okay, this is a function form, we've seen that earlier, where phi of x is a function with very sharp maximum, close to a delta, at x equals 0. Okay, so now you have this result, you have this extra assumption. It says making the change of variables xi plus eta equals v and xi minus eta equals w, the integration can be carried out. Okay, let's verify that. Okay, so here we have this this equation. Let's just call it star. So we need to evaluate the double integral. The double integral in star. How do we approach that? Well, the double integral in star, let's just call it I. Okay, let's call I to be the integral from 0 to t, integral from 0 to t, e to the beta xi plus eta, and then times a of xi times a of eta d xi d eta. Okay, sorry, I'm losing my voice. Okay, so what do we do to solve this integral? This is a classic problem in multivariable calculus, right? So first of all, let's replace the function, correlation function, by phi of xi minus eta. Oh, the cat is angry. Okay. So we need to make a change of variable. So do a change of variable, say, here, let's do a change of variable as promised. Xi plus eta equals v. And xi minus eta equals w. Okay, and we now need to, first of all, rewrite the range of integration and the new area element. So here, for that we use the change of variable formula in multivariable calculus. So this will be integral, let's just put it this way. I'll put the bound later. Okay, first of all, the integrand now becomes e to the beta v times phi of w. And then it should be followed by a Jacobian term, which is d over, let me think, so it's dv w over d xi eta. Absolute value, dv dw. Okay, so we need the Jacobian. Let's calculate the Jacobian. dvw over d xi eta is a determinant dv dv over d xi, dv over d eta, dw over d xi, dw over d eta. And this is a linear transformation, so it should be pretty easy. This is 1, 1, 1, minus 1. So you end up getting a minus 2. So the absolute value of that would be 2. Okay, but what is the new bound of integration? And for that, you would have to draw the diagram. Right. So actually, we need more space. Okay, we need more space. So initially, the integration region is a square. This is xi-axis, this is eta-axis, it's a square. Both are from 0 to t. Okay, so, and now after the change of variable, you get a new region. A new region, okay, well, let's try to determine its shape, all right? So the new region is the VW plane, obviously. And we can say, let's try to get the inverse transformation, okay? Inverse transformation. Inverse change of variable. So adding the two equations gives us 2 xi equals v plus w. So xi is half v plus w. Subtracting the two equations, you get 2 eta equals v minus w. So eta is half v minus w. Okay, and so now you can use the original range or bond. So this is v plus w is greater or equal to 0, less than 2t, because xi is between 0 and t, and v minus w is the same, greater or equal to 0, less than or equal to 2t. Okay, so here you have v plus w greater or equal less than 2t is like this. This is 2t. Greater or equal to 0, that's like this. Okay, so here w is v minus 2t. Yeah, w is, hang on a second, the first inequality, the boundary case is v equals w. V equals w is like this. And the other one is w equals v minus 2t, which is like this. So this is a new region. This is a new region of integration. Yeah, that's correct. So this is a new region of integration. So how can we parameterize this? Well, hang on. So is there a convenient way to parameterize this? So when w absolute value is given, say if we fix w, then v is between, yeah, v is greater than w and is less than this line, which is 2t minus w. 2t minus w. And here, because you can just say it's because of symmetry, so it's v greater than w absolute value and is less than 2t minus w absolute value. All right, so that's the new integration region. We can say w ranges from 0 to t. Oh, actually, never mind. W ranges from minus t to t. This is minus t. This is t. W ranges from minus t to t, and v goes from, for each fixed w, v goes from w absolute value to 2t minus w absolute value. Okay? And the inner integral, so first of all, 2 can be factored out. Yeah, 2 can be factored out, and now you have the inner integral. The inner integral is with respect to v. So phi can be taken out. Phi of w is now here, minus t to t here. The integral from w absolute value to t minus w absolute value e to the beta t, beta v, e to the beta v times dv, and finally you have a dw. So the inner integral can be evaluated analytically. After all, it's just integrating a exponential function. So this gives us 2 times the integral minus t to t phi of w times 1 over beta e to the w e to the beta v from w absolute value to 2t minus w absolute value dw. So this is 2 over beta integral from minus t to t phi of w times e to the beta times 2t minus w. I hope I didn't make any mistake. Okay, minus e to the beta w. Okay, I hope this is all right. We check with the answer soon. dw. Okay, so what else can we say here? Well, phi is an even function. Phi is assumed to be an even function, and this function is also even because it only depends on w absolute value, so you can write it as the integral from 0 to t and 4 times 4 over beta phi of beta e to the beta 2t minus w, just positive w, minus e to the beta w dw. So that's the integral. Okay, that's the integral. So then combined with this factor, so yeah, this is the factor here. We just evaluated the integral though. So star now becomes the following. Times this result. This can be simplified further. We can multiply e to the minus 2 beta t inside. Get 4 over beta times integral from 0 to t phi of w e to the minus w times e to the beta w minus 2t dw. I hope this is okay. Let's check the answer. I have no hope. Actually, this is not okay. This is actually not correct. Huh? Where does this minus infinity to infinity come from? That's crazy. Well, the integration is extended to infinity because, okay. Does that change this thing, though? Does that change this thing? So here we're extending this to infinity. So what is going on here? So this function, so the correlation function, this is phi of, yeah, so this is the correlation function. This is only significantly different from 0, very significantly different from 0 when in the original integral, when eta is close to xi. So basically only near the diagonal, only near this diagonal where the integral is almost is the most significant, right? And now just t gets swapped to infinity. What's going on? Okay, so can we take t tends to infinity here? If I take t tends to infinity here, what happened? And you get a 0 here. Interesting. What is going on? How do you get that integral? So this is, it's kind of interesting. So you just get the integral of phi 1, but isn't that supposed to be, okay, so this is just phi 1, integral of phi 1, and then this is tau 1 times this factor here. Okay, and then what next? Recalling that equipartition energy theorem requires, yeah, because of half mu squared average is supposed to be half kbt. So u square average is supposed to be kbt over m. Okay, and then what happened? So tau 1. So you can actually solve for tau 1. Wow. And you get the okay, so still, let's try to fix this integral because this is important. I don't know, like, how do we say, okay, so yeah, the double integral, suppose let's just change t to infinity, okay, see what else needs to be changed, where t is changed to infinity. Okay, so that should make the integration region a bit easier. Change to t to infinity. What's the justification for that? It says the integration limit in the definition of tau 1 extended to plus or minus infinity because of the thing is I think this should be the last step. Earlier you should still keep t, no? It's awkward. So is there any mistake here? And you just check e to the beta of v times phi of w times the Jacobian. Oh, actually, this Jacobian is wrong here. Because it's dv/dw, then it should be reversed. My goodness, I'm silly. This is should be xi and eta should be on top. This is a big mistake. I haven't used this formula to do calculus for ages. So yeah, this is wrong, okay? So this is 1/2 should be. So this should be 1/2. Everything becomes 1/2. So in the final step, 1/2 cancels. It's just because of the evenness. Okay, so there's that. That's a mistake. Yeah, this change of variable formula needs to be fixed. Okay, and now what else? Integration with respect to v first, yes. For each fixed w, v is between v is less than, yeah, so v is less than 2t minus w absolute value. That's right. And v is greater than w absolute value. That's also true. You have this integral 1 over beta e to the beta v from w absolute value to 2t minus w absolute value. Okay, this integral just becomes e to the beta 2t minus w absolute value minus here. It all looks okay, huh? What shenanigan is done here? So apparently you can get rid of the exponential. How is that even possible? Okay, so you have this e to the, yeah, the t cannot be taken to infinity from the start, no? Because otherwise this feels a little bit weird. Hmm. Phi1 of w. Okay. Hmm. I didn't make any mistake here. This is the same as in the text. This one. 1.28 is given. 1.28, yeah, 1.28 is correct. And now we integrate that, replacing this by phi1, which I just wrote phi. And new variable is there a sign mistake here? Here, a of t1 times A of T2 average is phi 1 of T1 minus T2. Okay. Xi minus eta is W. Xi minus eta is W, yeah, like this. And then you, gosh, I have no clue. It does not look like the result promised at all, huh? So basically, what went wrong? 1 over beta taken out the front. Like at this step, here, at this step, maybe let's try breaking the term into 2 terms. Can we try that? Here, let's say you got 1 over beta, 1 over 2 beta, integral from minus t to t phi of w e to the minus beta w absolute value dw, and then you take, for the first term you can take out the e to the beta 2t, e to the 2 beta t, yeah, that's possible. And then minus 1 over 2 beta integral from minus t to t phi of w e to the, not minus but plus, beta w absolute value dw. But the thing is, you can never just simply get rid of the exponential factor. I don't know where on earth does this come from. How come there's no exponential in here? That's crazy. Making the change of variable, integration can be carried out. Okay, so okay, I think I'm gonna fix this later. Okay, we're just gonna fix this later, and then the idea is, in the long term, what happened? In the long term, the first term cancels out in the equilibrium, right? This is the result in statistical mechanics, in equilibrium statistical mechanics. So in the long term, the first term goes away, and it's supposed to be just here. If you take the limit, the left-hand side, on the right-hand side, only tau 1 over 2 beta survives. So tau 1 can be solved. It's 2 beta kbt over m. So tau 1 is now solved. Substitute that back into the equation. So this way you get the full expression for the mean square velocity of the Brownian particle. But this is still very puzzling. How come the integral, it doesn't seem to work? Okay, anyway, I'll fix that later. Okay, I'll fix that another time. So now you have this result for the mean square velocity. And we also make an extra assumption that A of t is Gaussian. It is then possible to show that the random quantity, so that basically is u minus its own mean, is also Gaussian. So, of course, this begs for an explanation why u is also Gaussian. So you can think of this way. This is the expression of u in terms of a. And on the left-hand side, you have a constant, I mean non-random function. So u minus u naught e to the minus beta t is e to the minus beta t times the integral from 0 to t, e to the beta xi, a of xi, d xi. So because on the right-hand side, this is a linear function, a linear functional, in fact, a linear transformation of a of xi. And we know from basic statistics that a linear combination of Gaussian is still Gaussian. And this result actually survives in integral sense as well. So That's why on the right you also have a Gaussian. It is possible to show that, and perhaps currently, I mean, we can just accept this as given, and later on when we discuss stochastic integrals, we will actually show this. Later we'll show this. So right now the heuristic explanation is just that it is a linear combination of Gaussian random variables. Okay, assume that a of t is a Gaussian random variable for every t. That is to say, assume a of t is a Gaussian process. It's a Gaussian process, then you can show that a linear function of a Gaussian process is still a Gaussian random variable. So now what we have the mean and the variance. This is the mean of u, and here you have the variance, or the second moment. So the second moment is now known. You can find the variance, right? And you use the Gaussian formula, and you get the full distribution. And this is the distribution of velocity given the initial velocity. There's that. Okay. So yeah, that's the velocity distribution. Having derived the velocity distribution, what's interesting is that when you let t tends to infinity, you get a limit. You get a stationary distribution. This is called a stationary distribution. When you let t tends to infinity, is there a formula here? Okay, it didn't say. Okay, it didn't say. So right now, I mean, I do plan to finish at 7. So how long are we dealing with here? No, I mean, I will try to decide the level of details I'm going to go through. Okay, so we still have plenty of time. So I'm going to go through the rest. Okay, and later today, perhaps the next time I'll fix this integral. Okay. So, all right. I was saying, as t tends to infinity, this Gaussian density also has a limit, has a non-trivial limit. Is a non-trivial Gaussian, m over 2 pi kbt square root times exponential of minus m over 2 kbt. On top you just get u squared. Yeah, that's it. This is the Maxwell-Boltzmann distribution in equilibrium statistical mechanics. So you actually recovers the equilibrium statistical mechanics. This is, as time tends to infinity, this is the Maxwell-Boltzmann velocity distribution. Based on, for example, this can be derived from equilibrium statistical mechanics based on maximizing entropy argument. So there's a nice connection between this and classical equilibrium statistical mechanics or thermodynamics. Let me just show that real quick. Maxwell-Boltzmann distribution. I mean, we don't assume this, okay? We don't assume you know statistical mechanics in the series, but this is a well-known result, okay? This is a very famous result, so I think it's worth mentioning. As t tends to infinity, the velocity distribution here. Oh, this is actually the distribution of the speed. What about the velocity distribution? Yeah, so I mean, another way to check this is that you can calculate the speed distribution. Namely, you don't care about the direction anymore, and you can derive that. This is the velocity distribution. So anyway, having derived the velocity distribution, Ornstein and Ulenbeck proceeded to calculate the distribution of the displacement. So for the displacement, what do you get? For the displacement is just the integral of the velocity. X is the integral of u dt. So I think Professor Scott left as an exercise. You can get the actually here. Yeah, so there are some details here. Having this derived the velocity distribution, Ornstein and Ulenbeck proceeded to calculate the distribution for the displacement. The problem is to determine the probability that a free particle in Brownian motion, which at initial time t equals 0 start from x equals x naught, with velocity u naught will lie after time t between x and x plus dx. This is basically saying you want the conditional density for the position at time t. And it is clear that this probability will depend on x minus x naught only. That's the displacement. That's the size of the jump. And on t. Right. So starting with the velocity formula, right? You get the integration of ut. You get the position. Right. You get the position, and now integrating this partially. Hang on. There's got to be some steps that needs to be justified. Okay, so we'll skip this and we'll come back to verifying the details. So the idea is you're just going to integrate the velocity process. The velocity process is driven by the forcing term, a of xi. Right? And as a result, x of t also has an a of xi in there. Right, and then you just want to calculate the mean and variance of this thing. The mean should be 0 indeed, because it only has linear term of a. Right? Linear term of a after integration vanishes, and then you need to square this thing and get the new mean. Right? So taking the mean gives this. Okay. So what does this say? What does it say? S is the size of the jump. The size of the jump is, in fact, it has a limit. It has a limit. So, given the initial velocity of u naught, the size of the jump on average will tend to, let's look at the asymptotics, u naught over beta by a fixed amount. It's not going to keep going forever, and this is because of the linearity in the differential equation. So basically, due to the assumption that the drag is linear, is Stokes' law, the drag is linear, there is a maximum displacement. There's a maximum displacement because of e to the minus t tend to 0. There's an upper bound. So, okay, that's cool. And now you square this. You square this s. Here you square this s, and then you also take the moment for that. Square this s, and the calculation is tedious, but should be doable. So we're tau 1, right? Tau 1, once again, tau 1 is quite interesting because tau 1 is the area under the correlation function. This is just the integral of phi 1. So it's just supposed to be, which I failed to get, okay? So basically, I need to fix this. So tau 1 also appears in the statistics for the displacement as well. Right? So this result was first obtained by Ornstein in 1917. In a limit of long time, okay? In a limit of long time, then these terms, they all vanish. Actually, they don't all vanish. They tend to a constant. Okay, but the point is it will be linear in t. This is an asymptotic result. As t tends to infinity, those two terms are constant. But in the asymptotics, it converges to this is the long-term formula. So on the shorter terms, however, then you would have what? Then you would have a shorter term asymptotics, which is based on the Taylor expansion of e to the t. Actually, let's do that. Actually, let's should do that. Okay, so here we have problems. Okay, basically, and now let's do this part of the math. Perhaps we'll do it later. Okay, perhaps we'll first go through the overall math and then we'll come back. Okay, so basically, here for short-term asymptotics, the mean displacement is linear in time. This is highly interesting because the mean displacement in long time is 0. According to Einstein, Smoluchowski, and Langevin, that's 0. But here, in the short time, this is u0 times t, and the mean square of the displacement is quadratic in time. Once again, it should be based on the Taylor expansion in e to the beta t. So what I mean is e to the minus beta t equals 1 minus beta t plus beta squared t squared over 2 factorial. And you just keep the leading term and get this. I.e. the motion is uniform. The motion is uniform in u0. So that's kind of interesting. So basically, as if there's no external forces, right? If in the short term, the particle behave as if there's no external forces at all. Taking the second average over u0, second average of u0, that is the distribution of, so basically here you first have the conditional expectation, and now you take the expectation over u0. Right, taking the expectation of u0, the distribution of u0 should be 0. Right, otherwise there will be bulk motion. u0 is the motion of a Brownian particle. We know that on average there is no motion. Right, the motion all cancel out. So u0 have an average of 0. And oh, by the way, this notation is the average of the average. Yeah, that's gotta be. It's the average of the average. So yeah, so the second average is averaging over u0. So that's the. This is what it means. Here, yeah, because it's linear in u0, so u0 has average of 0. So S double average is 0. And here, in this expression, if you take the average over u0, average of u0 squared is given by the equilibrium statistical mechanics, kBt over m, and you just simplify. All right, you just simplify and get this. Okay, so the calculation of higher powers proceeds similarly. In this way, we can show that the variable s minus the mean, right? S minus the mean. This is S minus the mean. It's Gaussian distributed too. So position is also Gaussian. I mean, we already explained the reasoning behind that, because as I said, A of t is assumed to be Gaussian, right here. Remember, A of t, the fluctuation is assumed to be Gaussian. And the velocity is a linear transformation of Gaussian, therefore it is Gaussian. And well, the displacement, which is also integral of Gaussian, is still Gaussian. So for Gaussian, if you know the moment, then Gaussian is fully characterized. Of course, this is a horrendous expression. Okay, but after all, this is a full distribution, so thanks to the Gaussian assumption. The Ornstein-Ulenbeck paper contains more than the results described here. For example, they re-derived the equation using what is called the Fokker-Planck equation, which we shall meet later in chapter 6. They also consider the effect of external forces. So for example, there's a harmonically bounded particle. So imagine there's also a restoring force. This is a harmonic oscillator equation with a drag term, and also the random force term. Okay, so this is the extension of the original Langevin ODE. So now you have basically this is perhaps the first thing you should try when it comes to considering a potential well. So you just use the linear restoring force. Okay, and so although the approach of Langevin was improved and expanded upon by Ornstein and Ulenbeck, some of the fundamental problems remained. Basically, the differentiability. So whether this actually is mathematically meaningful. As Doob pointed out in the introduction to his famous paper in 1942. So Doob, famous probabilist, actually let me go show Doob. Doob decomposition theorem, yeah, in the serial martingales. So Joseph Doob. So it's one of the principal architects of modern measure-theoretic probability. Building on Kolmogorov axiomatization of probability, he established a rigorous framework of continuous time stochastic process, developed martingale theory into the central method of probability, and pioneered probabilistic potential theory. So potential theory was about the study of Laplace equation. It's a PDE. It's a PDE. So classically, potential theory comes from Newtonian gravity as well as electrostatics. This is the Laplace equation. Hang on, where's the Laplace equation? There's not even a Laplace equation. Okay, it doesn't matter. And it turns out that the Laplace equation has also interpretation in random walk. So that's pretty awesome in the Markov chain. Modern potential theory is also intimately connected with probability in the theory of Markov chain. In the continuous case, it's related to analytic theory. Oh, nice thumbnail. I know where that is. Yeah, it's in the Wikipedia. So Ornstein Ulenbeck, also related to electrical network, pretty cool stuff. So Joseph Doob, he introduced martingale, did extremely rigorous mathematics. So there you go. Joseph Doob passed away in 2004. Age 94 years, wow. Actually, Paul Hummus was one of his students. Whoa, that's awesome. That's crazy. Paul Hummus was a student of Doob? I didn't know that. So yeah, this is by the way, we talked a lot about the Kolmogorov's axiomatization, the Russian school. But in the same time, the French as well as the American school are also pretty strong. In 1933, Kolmogorov provided the first axiomatic foundation for the theory of probability. Thus, the subject that has originated from intuitive ideas suggested by real-life experiences suddenly and studied informally suddenly became mathematics. Probability theory became measure theory with its own problems and terminology. Doob recognized this would make it possible to give rigorous proof for existing probability results, and he felt that the tools of measure theory would lead to new probability results, and indeed this is the case. Okay, so he basically, Kolmogorov axiomatized probability and did fundamental work such as Markov chains. Doob gave a general theory. Joseph Doob gave a general theory of stochastic processes based on measure theoretic probability. Right. So he wrote the book Stochastic Process. It was published in 1953 and soon became one of the most influential books in the development of modern probability theory. Okay, yeah, so, and he wrote a book over 800 pages called Classical Potential Theory and its Probabilistic Counterpart. The first half of the book deals with classical potential theory, and the second half with probability theory, especially martingale. Doob showed that his favorite two subjects, martingales and potential theory, can be studied by the same mathematical tools. How awesome is that? Joseph Doob. Okay, so yeah, when we come to, of course, in the mathematics of finance or stochastic calculus for financial mathematics, we will study martingale for sure. In fact, the very first thing that we will study is martingale. Okay. So basically, I was saying the stochastic series will be rotated between for physicists, for financial math, and for engineering. Okay. Anyway, so Doob has this to say about Ornstein and Ulenbeck. the purpose of this paper, okay, this paper, famous paper 1942, the purpose of this paper is to apply the methods and results of modern probability theory to the analysis of the Ornstein-Ulenbeck distribution, its properties and its derivations, etc. A stochastic differential equation is introduced in a rigorous fashion to give a precise meaning to the Langevin equation for the velocity function. This will avoid the usually embarrassing situation in which the Langevin equation involving the second derivative of x is used to find a function, is used to find a solution x of t not having a second derivative. So, in the ordinary sense, this is meaningless. So, this is the famous remark by Du. Actually, you know what, guys? Let's take a look at his famous paper, Annals of Math, 1942. Du paper 1942. What is a stochastic process? Is this is Taylor's and Francis, but this is paywalled. Is there a... This should be in public domain, no? Actually, this is different. Okay, so this one, huh? Is this paywalled? Probably paywalled. All right, that's sad. It's paywalled. Okay, anyway, I can't show it now. Okay, so there's that. Obviously, there's something deep going on in terms of differentiability and integrability of the stochastic process. In particular, to make sense of Du's statement, we need to know what it means by differentiability in this context. This will be the focus of chapter 7. So there we'll actually define the differentiability, integrability, continuity of stochastic process. Okay, so what's next? So here, of course, we are only dealing with a very special case of stochastic process, the Brownian motion, although a very rich one. And this is one of the, I think you can say this is the biggest goal. Okay, this is the biggest goal of the series stochastic processes for physicists, is we wish to get to a Fokker-Planck equation. Last time we showed a dependency diagram. This is in chapter 6. There's a dependency diagram of various mathematical tools we use to model Markov process. Hang on, where is that? Yeah, chapter 6, right here. So, for Planck equation, this is a derivation, we'll come to that. Yeah, there's the dependency diagram. So first, starting from Markov process assumption, you have the CK equation, Chapman-Kolmogorov equation. Assume stationarity. You get to simplify things a little bit, but still, this is still unmanageably complicated. It's a nonlinear functional equation. And now, assuming there's some assumption in so-called microscopic theory, you can reduce or approximate CK equation to the master's equation. Okay, so to assume you can get the master equation, and in the master's equation, making further assumption, you get the Fokker-Planck equation. So this is our principal goal here. One of the everyday tools in non-equilibrium statistical mechanics. And here, mathematically speaking, Kolmogorov equation, also known as Kolmogorov forward equation, is the same as Fokker-Planck's equation. Although the reasoning is a little bit different. Okay, the reasoning, the physical assumptions involved is a little bit different. Okay, so this one, Kolmogorov equation and Fokker-Planck's equation, are both PDEs. The original CK equation is a functional equation, and the master's equation is a differential integral equation because it involves the derivative of the unknown function as well as integral of the unknown function. For the most circumstances, this is still unmanageably complicated. and reducing it to PD is a great simplification. Okay, so this is where we are trying to get to. After all, this is what this series is about. It's about the method of finding solutions, actually solving solutions. We're not super involved with proving existence and uniqueness. Although the smoothness, right, the differentiability, that kind of thing, we're still going to discuss because it changes a lot of things. Okay, anyway, here, going back to the first chapter, right? So, what's the relationship between Ornstein Ulenbeck's work to the rest of the course? Here. In addition to clarifying the assumptions left implicit by Langevin and permitting a generalization of Langevin's approach, Ornstein Ulenbeck provided a mathematical connection between, okay, this is cool, the connection between Einstein, the kinematic approach by Einstein, and the dynamical approach by Langevin. That connection will be made explicit in chapter 6. Okay, awesome. All right, so this is the outline of the book. We briefly talked about it in the first episode, but let's just take a look at it. That was in my own word, but let's take a look at what Professor Scott has to say. In the broad strokes, the outline of the book is as follows. First, the fundamental concepts are introduced. Chapter 2, random process. So these are the fundamental definitions in the stochastic process from a non-measure theoretic point of view. Okay, the idea of classical probability theory are extended to random variables, to the concept called random functions. We particularly focus on a special class of stochastic process called stationary process. Stationary process is also super important for time series analysis. Classical time series analysis, like the ARIMA method, autoregressive, which stands for autoregressive integrated moving average. And ARMA process, under certain situations, are stationary. So these are fundamental for time series analysis, a topic in statistics. Okay, anyway, that will be used throughout the course. Okay, stationary process, stationary assumption will be used throughout the course. Okay, so for example, in engineering, this is a great restriction. So that's why we also will have a separate episode/series on stochastic process in engineering. Because over there, stationarity is a great restriction. This is a side tangent, but basically in engineering we care about two things, two main things. Okay, signal analysis as well as control, optimal control. So in signal analysis, there was the problem of so-called filtering. It's quite literal. You want to filter out the noise to get the information you want. And there are two main filters called Wiener filter and Kalman filter. Wiener filter came earlier, which built on the stationarity assumption. Kalman filter does not rely on stationary assumption. Okay, anyway, so we're going to be dealing with mostly stationary processes here in this course. Particular attention is paid to the second moment of stochastic function at different values of times, called the correlation function. Second moment. So basically for stationary processes with finite second moment, there is a nice theory called the L2 theory. This kind of process called L2 process. And over there you can borrow a lot of the Hilbert space theory from functional analysis. You can do, for example, orthogonal projections very efficiently. So this only requires second moment information. After the fundamentals have been established, we examine how stochastic processes are classified, okay, which particularly focus on the most common process appearing in the modeling of physical systems, the Markov process. Okay, Markov process. Markov process, the way I described it last time, is that it is a direct generalization of ODEs, ordinary differential equations. So it's just ordinary differential equation with uncertainty. Now, ordinary differential equation has a lot of theorems called the existence uniqueness theorem for the initial value problem. Basically, given the initial state, you can determine the trajectories afterwards. And Markov process is similar. So given the initial state, you can forget about the history. So Markov process is the most commonly used stochastic descriptor with the property that the future state of the system is determined by the present state, and not any state in the past. This is a strong requirement, but it is often approximately satisfied by many physical systems and allows for useful coarse graining of the microscopic dynamics. Actually, you know what? I'm not a physicist, and I don't think I can explain this term very well. Let's go check that out. What is coarse graining? What I can say, however, is Einstein's choice of selecting the time interval tau is a classic example of a coarse graining. Here is also mentioned in this sentence. Shmolechowski's conceptual framework is ideal for many physical applications. This is Shmolechowski's idea. And here we say many physical systems with appropriately chosen coarse graining of the observable time scale can be represented by a Markov process. Right. So the time interval tau, interval length tau, in Einstein's theory, this is a typical example of coarse graining. Although I'll have to look up the term precisely in physics literature. Why don't we just do that now? Coarse graining in physics. Coarse grain model. So coarse graining modeling aimed at simulating the behavior of complex systems using their coarse grain, aka simplified representation, are widely used in molecular modeling of biomolecules and various granularity levels. Okay, can we give an example? Coarse graining and fine graining in statistical mechanics addresses the subject of entropy S and thus the second law of thermodynamics. Okay, can we give a more, wow, coarse graining? What's the AI? I mean, this is not super descriptive, right? It jumps between very vague description to super technical description. Is a method that simplifies complex system by grouping many small parts, like individual atoms, into a single larger pieces called beads. Right? So, as we said earlier, the time scale coarse graining works kind of similar, right? So, in the time scale tau, in Einstein's time scale tau, it is still large enough for a large number of collision to accumulate their effect. Okay, so it's still much larger compared to the frequency of the forcing term. Okay, so there's averaging involved. Fast and small movement are smoothed out or ignored. Okay, so this is, I guess, a more helpful description. Here, here's another note on coarse graining. Basic types of coarse graining. This is a central idea in statistical mechanics. Ernfest introduced a special operation introduced by Paul and Tanya Ernfest. They're a couple, a physicist. The coarse graining. This operation transforms probability density into a phase space, into a coarse grain density that is piecewise constant function, the result of a density averaging cells. Okay, I was thinking about time. Renormalize, I don't know, actually. I'm very ignorant when it comes to statistical mechanics. I've also heard of the term renormalize, but from what I know, renormalization is a mathematical technique, whereas coarse graining is a physical modeling choice. Okay. Anyway, so going back to the Markov assumption of physical process. So it all really depends on what you observe and what time scale are you observing. Okay. The mathematics don't tell you that automatically. It's up to the modelers to decide. So what process can be treated as Markov? Okay. Anyway, coming back to the outline of the book, where we're heading. Okay. This is okay. So here, the evolution equation for the probability distribution of Markov process is often called the master's equation. So that's the master's equation. It tells you how the probability distribution of the Markov process evolve over time. Typically, this is as we said earlier, it's a differential and integral equation. A difficult equation to solve exactly. The remaining chapters, to a large extent, are methods of approximating the master's equation. So Fokker-Planck equation is a way to approximate the solution of master's equation that is more amenable to solutions. Okay, cool. Once Markov process and their evolution equation have been derived, we examine in more detail solution methods and the kinematic formulation of Einstein. Chapter 4, solutions of the master's equation. Briefly discuss exact solution method. In most cases of interest, the master's equation is too difficult to solve exactly. We examine the most popular approximation method, stochastic simulation. And actually, you know what? I think I'm going to skip chapter 4. I'm going to skip chapter 4 and go directly to Fokker-Planck. And I'm going to skip chapter 4 and 5. And if we have time, we'll come back to 4 and 5 and other methods. Okay, so these aren't needed for deriving the Fokker-Planck equation. So our plan is to do chapter 2, and then even skipping some of the chapter 2 stuff, and then go to Markov process, and then go to, this won't follow the book linearly, okay? I'm just taking the path of least resistance, the shortest path to Fokker-Planck. So this is like a speed run to Fokker-Planck. I have no clue. So, I mean, because as I said, I'm not a physicist, okay? So, once again, this series do not assume knowledge of physics because simply I don't know much physics. So let me actually just search it up. So, zoom effect, right? Is that what you're saying? I have no clue. Hang on. It's not in there. Hawk process. You mean Hawk's process? Okay, this doesn't show up in, but I do know Hawk's process. Actually, not Hawk process, but Hawk's process, right? This is like a self-exciting process. You know, somebody requested me to do a live on this one, Hawk's process. Is that what you're talking about? EJ? Once again, Hawk process is a different beast. It's not Markov. Okay, this is not a Markov process, but it has this. So basically, it's kind of like a Poisson process, but the rate. Okay, yeah. So the Hawk process, yeah. So the rate has this self-exciting feature. So the thing is, the event. The occurrence, yeah, here the occurrence of an event increases the likelihood of another event. This is not a Markov process, okay? But the Markov process only depends on the current state. But here it depends on recent history. It depends on recent, actually it depends on all of history to be exact, but it's more influenced by recent history. It's like you can model this, you can use this for model earthquake. And also social media dynamics. Like a viral video came out and suddenly it got shared a whole lot. Right? This is the point of Hawkes process, which is a interesting topic on its own, and I'll have to do this at some point because, well, I did agree to do one. I mean, although my understanding of it is very much at the surface level, I'm not an expert on Hawkes process either. Okay. Anyway, this is not a macro process, and it's beyond the scope of what we're doing here. Beyond the scope of Fokker-Planck equation. This is such a big field. Stochastic process is so large. If it is at least as large, if not larger than PDE. You know, the techniques for specific classes of processes aren't particularly transferable. Okay, so anyway, perturbation expansion of the master equation. This is of course very interesting, and of course perturbation expansion is on its own a super interesting topic. But we're gonna put it aside. Okay, we're going to put it aside in our first, so to say, speed run to Fokker-Planck equation. We want to get into PDE stuff as soon as possible. These are more specialized techniques. The linear noise approximation of Van Kampen is robust and widely applicable analytic approximation for the solution of the master equation. The Fokker-Planck equation, this is the PDE with drift that governs the entire probability distribution. A generalization of the diffusion equation used by Einstein in his study of Brownian motion. A popular analytic method of approximating the evolution of macro process. There are some ambiguities and essential difficulties associated with this method when applied to a system with nonlinear transition probabilities. Okay, so as you can see, the book, overall the flavor of the book is very much grounded in physical applications. It's all about deriving a method with its assumptions clearly stated, physical assumptions in particular clearly stated, and not much when it comes to mathematical justification. So perhaps this is closer to actual physics research. Okay, before returning to the dynamic SDE method of Langevin, Ornstein, and Ulenbeck, we must formulate the calculus of random functions. So this is the stochastic calculus. This book in particular do not spend a lot of pages on stochastic calculus. Okay, the fundamental ideas are introduced, but for example, it does not even derive the Ito's lemma, which we do have a video on. How to find phi properly? You know, okay, this is a great question. So typically, from what I read, phi is typically taken as exponential. In the Hawkes process, it's taken as exponential function. I mean, I don't know a whole lot about this, but typically this is taken as exponential. It's a user's choice. Often you take exponential. So this way, tk is the event of occurrence. So the idea is phi is an exponential decaying function. The longer, say, the current time compared to the previous event time, the less of an effect that previous event has on the arrival rate. Okay, so phi is pretty much a user choice. Anyway, okay, so this is a side tangent. Okay, so let's come back. So stochastic calculus, big topic, of course, ongoing series. I haven't yet abandoned it. Some people suspected I abandoned stochastic calculus. Not at all. It's just that earlier I figured I'm having difficulty with making videos. Too much going on in life as well. So I figured, you know what, I'll do more live streams to connect with my audience, and in the process we'll prepare more material. So hopefully before formal videos came out, I can still have some output, right? Chapter 8 is random differential equation, stochastic differential equation. And now you can analyze them a little bit more, although still at a non-rigorous level. So particularly focus on numerical simulations and analytic approximation of solutions. And overall, it is very rare for SDEs to have analytic solutions. Okay. Anyway, so now you have more specialized topics, macroscopic effect of noise, special topics. Some of the additional topics included, which are beyond the scope of the course, perhaps of interest to some readers. And these are the references I was talking about. So these two books are strongly recommended. Well, I would say the first one is perhaps more friendlier. It's friendlier than the second one. Handbook of Stochastic Method by Gardiner. Extremely well cited book. I think well over 10,000 citation or something. So as a claim, it's a handbook, so it's not exhaustive, and it has no exercises, no explicit exercises, but it has a great number of examples actually. And right now, it's just called Stochastic Method, not handbook anymore. It's just called Stochastic Method. So quite big revision. So the fourth edition of the book is a lot more expanded. Okay. So do make sure you get the latest version. This is old. So this one, the second one by Van Kampen, Dutch physicist, he was mentioned a few times already in the text. This one is, I would say, in my opinion, okay, in my experience, even harder than this one. But this is actually meant to be a textbook, so it has more exercises. But good luck, okay. This is, this one is like land on Lifshitz. This one, the stochastic process in physics and chemistry. This one feels to me, it gives me a lot of the land on Lifshitz vibe. He doesn't shy away from making emphatic and unambiguous statement. A kind of question: if we already set probability to some form, how can we say stochastic? I feel whole stochastic is just obey some rule. Like, I'm not sure what you mean, but basically, yeah, as actually Van Kampen said in his book that probability theory is all about transformation. It's all about just some transformation. So if you say, if you have, I mean earlier, right? We've seen that earlier today. We only assume the probability distribution of the forcing function, and then the rest is just a deterministic function. You see, U is a deterministic function of A of xi. Assume you know the full trajectory of A of xi, then this is a fully deterministic function. Right? The source of randomness is here, and the rest is just calculus, finding mean and variance and stuff. Right? So is that what you mean? Yeah, in a sense, even as Van Kampen mentioned in his text, in his view as a physicist, probability theory is just a theory of transformation. Anyway, so he doesn't shy away from making emphatic and unambiguous statements that help in learning the material. The exercises are excellent, difficult, and rewarding. Okay, a good supplemental text in statistical mechanics by Reef. Okay, so that's some background, I guess, domain knowledge. Yeah, fill in the steps that connect equation 1.28 to 1.30. This is where we struggled, right? 1.28 to 1.30. We didn't get the integral. 1.28 to 1.30. So we failed exercise 1. I mean, I failed exercise 1. So we'll see how to do that, okay? Anyway, So yeah, why don't we just stop right now? Because I'm getting a little bit tired, and I gotta eat. It's 6:30. It's about dinner time. So I'll just stop right now today, and next time we will do chapter 2, fundamental of stochastic random processes. Okay, random processes. And actually, you know what? Let me just briefly take a look at chapter 2 and see what we can skip. Okay, I want to get to Fokker-Planck as quickly as possible. So here in chapter 2, this is unskippable stuff. Okay, this is unskippable. Random process, basic concept, this is unskippable. So unskippable moment, unskippable stationarity, unskippable, perhaps ergodic theorem is skippable. We'll briefly talk about the ergodic theorem. Going down here, spectral density, this is skippable. So we won't talk about spectral density, although quite interesting, but we'll come back to that later. Fluctuation dissipation, we'll come back to that later. I just want to get to Fokker-Planck as quickly as possible. Johnson noise, they're all interesting topic, but we're going to skip those. Okay, as a first reading, so I'm trying to speed run to Fokker-Planck once again. Okay, I'm not saying these aren't important. Markov process, this is absolutely needed. This is unskippable. So perhaps we'll do random process and definition of Markov process. CK equation is definitely within reach next time. Markov process, CK equation, which is essentially a law of total probability. So there's that. Okay, and here we are. It's really like a strong correlation system study way. Strong correlation? What do you mean by strong correlation? We do assume the certain form of the correlation function. Like correlation function will play a strong role in the spectral density part. Actually, for engineering, we will talk a lot about spectral density. It's got connection with Fourier analysis and whatnot. Okay, Master's equation. Yeah, so I'll try to get to master equation next time. I'll try to do random process, CK, and master's equation next time. I think that will be great progress. And after we derive master equation, we'll see some simple examples, like burst and dash process. And then immediately switch to Fokker-Planck. Just jump straight to chapter 6. Should be okay. So this mini series can be finished in 4 episodes, which is about like 16 hours. So yeah, chapter 6, Fokker-Planck equation. So you see, it started from this, starting from the master's equation, and with some new approximations involved, new assumptions. Right. There you go. And that'll be it. That'll be it. The Kolmogorov equation derived, and that's the most important thing. And perhaps later, when we study more about PDEs, we can see some actual solutions. Even though, like, this is a great simplification, the PDE is still highly non-trivial to solve. All right, so that's it for today, and I think we have a lot to look forward to. And as mentioned, this Saturday we will kickstart stochastic differential equation. Applied stochastic differential equation, or stochastic differential equation for beginners, whatever you want to call it. I'll try to think of a title for the live stream as well as the thumbnail, and I'll see you guys next time.